Thank you very much for coming to this tutorial. It's a relatively small group, so I would encourage people to interrupt me and ask questions as I go. It's more important than that I get you interested in this area and convey a subtopic that you can take home and do more research in this area than to cover everything that I have today. So feel free to ask me questions. So the way I have structured the tutorial is that there will be 3 parts to it, each one roughly about 50 minutes to an hour. And in between those 50-minute segments, I was planning on 10-minute coffee breaks. But Daniela just told me that coffee will be here at 3:20. So that's right in the middle of what I was planning originally. So we'll see what we can do, and we'll probably take a short break right when coffee comes out so that you don't miss out on the coffee break. Okay, so my name is Saikat Guha. I work for the University of Arizona in Tucson. My background is at the intersection of quantum optics and information theory. So my apply tools from information theory and quantum information theory to understand fundamental limits in optical communications, optical sensing, pretty much wherever light gets used, trying to understand the fundamental limits by treating light as a quantum mechanical object rather than working with a classical description of light. So my goal in today's tutorial is to talk about optical communications specifically and about classical optical communications. We will still be sending classical data encoded in light, but we will be looking at the fundamental capacity limits and how you can go beyond the Shannon capacities associated with the traditional noise models that come from some of the standard optical communication receivers. Okay. So let me start with a high-level message from this tutorial. So if you just take home this slide and the message here, I think that would be the most important thing I would like to convey. So let us set some notation first. So I'm going to use the term modulation for converting information that is in the classical domain, electrical domain, into the optical domain. Okay, so that's modulation. I'm not going to distinguish between optical and microwave. It just so happens that some of the receiver types that we are going to talk about today are much more relevant when you are working at optical frequencies because you are, for instance, you are short noise limited. But in principle, there is no difference between the quantum domain being at a certain frequency or the other. I'm going to use the word detection for what some people also call transduction. So that's the process where you convert the information bearing light into the electrical domain. So that's right when you detect and convert the optical signal into an electrical signal. Sometimes you would see the word detection being used as a corollary to post-processing. So I'm not referring to that. Detection is that process where you convert from light to electrical domain. And then post-processing can follow detection. A receiver can include any pre-processing of the information bearing light, followed by detection, followed by post-processing. So that's what I'm going to be using the word receiver for. So receiver contains a detector, but it can contain other things, for instance, before the detector and after the detector. So noise is a fundamental aspect of detection. So no matter how you choose to detect light, there will be some amount of noise associated with it. And there is a minimum amount of noise that is governed by physics. Depending upon the way you choose to detect light, the statistics of the noise can be different. Okay? So the actual statistics which determines the P of y given x, the y part, this is the part that comes as a result of the detection. So most of Shannon theoretical work starts from that stochastic description of the channel, P of y given x. But we are going to try to zoom a little bit more into it and see the origins of that y. Okay? And there are many types of standard optical detectors, and we are going to talk about direct detection, homodyne detection, and heterodyne detection. These are some of the standard ways of detecting light. And each one has its own ramification on how the noise statistics gets added to the signal that is being detected. Now, if you know something a priori about your information processing task, for instance, in this case, you are trying to send information reliably by encoding them in light, then oftentimes you can do something before you detect that light. You can do something in the optical domain. Sometimes that may involve some non-classical transformations in order for you to present that information bearing light in the most favorable way to the detection noise that is yet to come. So because we know how detection noise will affect will get added on my signal, I can do something before that detection happens. So that's the most important thing that we'll be seeing more. This is the theme that will be coming multiple times through this tutorial. Now, quantum information theory or quantum estimation theory, these are tools. This tutorial is not about quantum information theory. A colleague of mine, Mark Wilde, gave a tutorial a couple of years back in ISIT. It was about quantum information theory. But here we will be using quantum information theory to understand the fundamental capacity limits of optical communications. And we will see that sometimes it is much easier to use tools from quantum information theory to tell us what that fundamental capacity is, but without even telling ourselves how to design that receiver in order to position that information in the most information favorable way. So that turns out to be a totally separate bottom-up task for which we have to apply our knowledge of quantum optics in synthesizing circuits involving known optical components and our knowledge of how noise affects in terms of those detectors being preceded by certain optical transformations that we will be talking about. Okay, so that's the theme that we'll be talking about today. And as you will see that by starting from some of the conventional channel models that come about because of the standard ways of detecting light, for instance, AWGN channel comes from homodyne detection, the Poisson channel comes from direct detection, for instance. The Shannon capacity is associated with all of these standard optical detectors or optical receivers in that case. They fall below the fundamental quantum limit to classical communications capacity. And in order to attain that capacity, that pre-detection processing you need to do often has to be a collective processing over an entire code word block as opposed to being on symbol by symbol. So that's the high-level message of this tutorial. Okay? So just to put it in pictures rather than words, so that's what I was talking about. So here you have your modulation, the physical channel. This is the channel that takes an optical signal to an optical signal at the receiver. And then the quantum or optical receiver that first could pre-process and then detect and post-process. And all of this together gives us our P of y given x, whose capacity we know from Shannon theory. Okay? So what we are going to do is to try to zoom in into this physical channel and ask ourselves the question, what is the capacity of just that quantum channel without making any assumptions on how you modulate or how you receive? And we'll be focusing mostly on this question mark here because of a reason I'll describe later, is that for the kinds of channels that we'll be talking about, lossy, noisy optical channels, that laser light modulation, traditional classical modulation, happens to be quantum optimal, meaning we only have to focus on this box. And the capacity that governs that fundamental limit is called the Holevo capacity. This is named after Alexander Holevo, was the Shannon Award winner of a couple of years back. And this number will be in bits per use of that channel, okay? So, and this will be higher in general than the Shannon capacity associated with any P of y given x for any particular choice that you made on both sides. Okay. All right, so let's go to my outline. So I'm going to start with about a 45 to 50 minute tutorial on classical and quantum information theory. And as I go through each of these topics, I will build up some concepts, sometimes not in full rigor. I'll give you references, and there will be occasions when I'll not derive to the very end, but I'll give you enough material that will suffice for you to derive that final result, and leave that as an exercise. Some of those exercises are actually open problems, and I'll point you to those when they are actually so, and a couple of them that I'll do in this lecture will be actually publishable if you were to solve those open problems. So and as I progress through these three parts, they will get progressively more complex. So the first part will be the easiest to follow, and then the second part will go into talk about optics and just about optical detection and state discrimination. And in the third part, we are going to put together our knowledge of quantum information theory and detection theory and optical detection to apply to optical communications. Okay, so that's the plan. I don't think I'll have time to get into secure communications, but we'll see how we do And if not, then I'll be happy to share these slides to whoever is interested in this audience. All right, so let's start with our part one, classical and quantum information theory. So these three gentlemen you see here, they are, so some of the work that I'll be talking about are, they come from some stellar contributions from all these three people. So Shannon, he started the field of information theory, and his starting point was a stochastic description of noise. So that P of y given x is the stochastic description of a channel. The P of x, the distribution with which a source output symbols, that's a stochastic description of a source. So all of Shannon's information theory is built based off of a stochastic description. It does not go into the physics-based description. Von Neumann did some early work on statistical physics motivated understanding of how you can encode information in physical systems. And a lot of von Neumann's work went into some of the early notions of entropy that appear in quantum information theory. And Holevo, followed by Schumacher and Westmoreland, they proved the first rigorous coding theorem that appears in quantum communications or sending classical data on a quantum channel. After that, there has been a lot of work on quantum information theory. Mark Wilde's textbook and Holevo's textbook, they are excellent references for results in quantum information theory. So I'm sure all of you in this room know about this, but I'm just still going to talk about some very, very basic stuff just to set notation, because we'll be using some of this notation as we go along. So we all know about Shannon's definition of entropy of a random variable, which is negative sum of the P of x log P of x, where P of x is the probability with which the source emits a symbol little x. And we are going to assume that the source is IID. So every time you interrogate the source, you get an independent instance of little x. If the source is binary, meaning it only produces one of two outputs, say 0 or 1, with probability p or 1 minus p, then the entropy is given by this function, h binary entropy of p. We are going to use this notation, h2 of p, as we go forward. And this h of x has an operational interpretation that Shannon proved in his data compression theorem, which I'm sure, again, all of you here know. X produces a sequence of n source symbols. So each one of these ones or zeros, they come out with a probability p or 1 minus p. And if p is not 1/2, then that sequence can be compressed to a shorter sequence. And the ratio with which you can compress it with an optimal compressor is the Shannon entropy. And we obviously have to use epsilons and deltas to make that precise, and this is exactly precise only in the limit that n goes to infinity. Okay? So, but this is the basic idea. But notice here, the one way to think about this source compression is that if I were to build a register where every block of my register, every bit of my register can only store a 0 or a 1, only one of two different things, then n times h of x is the number of such bins I will need in order to accurately describe an n-length sequence of that source. Okay? And we'll come back to this description later on. And another thing, obviously, that is true is that if x has a cardinality greater than 2, then the log base 2 of that cardinality is the maximum value of h of x. That's when the source is uniform prior. And when a source produces multiple symbols with uniform prior, then it cannot be compressed. So for instance, when p equals to 1/2, you cannot compress it further. Okay, so and this other complementary notion and operational meaning for entropy comes about in Shannon's channel coding theorem, where you have a channel that gets you from x to y. So this is the binary symmetric channel described by a single parameter p. The mutual information, which is the difference of the output entropy and the conditional entropy of the output given the input, which is defined like that, is the capacity of this channel, meaning that's the rate at which you can send information reliably per channel use, in the sense that there exists a way to encode your information at the input and decode the information at your output such that you can send these many bits per channel use. So noise does not preclude error-free communication, but we need error correction to achieve that capacity. Again, we all know about Shannon capacity here, but this is just to set notation. why do codes help? Why does coding help? Okay. So the intuition behind coding is that you have all possible 2 to the n binary sequences. So each of these binary sequences could consume n uses of the channel. So the channel, every time I use a channel, I send a 0 or a 1. Okay. But then I don't use all the 2 to the n binary sequences. I'm still using n uses of the channel, but I only use 2 to the k of these 2 to the n binary sequences such that they are spaced apart well enough such that if the channel noise pushes you around, pushes the code word around, then you're still able to push it back to the code word that was sent. So the sender and the receiver, they both know all these 2 to the n code words. So these black dots are, each one of these are sequences of n bits that are spaced out in the space of all 2 to the n binary sequences. Basically what Shannon's capacity coding theorem proof boils down to is that for any rate less than capacity, there exists a sequence of n comma nr codes with, this is dn is the minimum distance between 2 code words in that code, such that the probability of error of decoding the code, the message at the output goes to 0 as n goes to infinity. And the way I've shown this decoding here, this is the received code word, and you send it back to the code word that is closest to that received code word. And that happens to become the maximum likelihood rule for the binary symmetric channel. You can go look at the proofs of this, but the basic idea here being that you're spacing apart these sequences so that you can, that you are more tolerant to noise. Okay. So let's look at how a coded channel looks like. So this is just an illustrative example. So I have 1 out of 8 messages. So my messages are actually 3-bit long, but I encode the message into a longer sequence. So I'm just showing an example of a 633 code. So 6 is the length of the code word. So I'm consuming 6 uses of that channel. At the output of the channel, so now I'm coding to, this is my information stream. I chunk it up into segments of 3. So that 0, 1, 0 is right over here. That gets mapped to 1, 0, 0, 1, 1, 0. So that's your code word and so on. Channel introduces noise, and then you map it back using a decoder, and you get the decoded information back. Okay, so let's talk a little bit about quantum mechanics. So a quantum system has a description that is given by a vector if you know everything about that quantum system. So that vector it's a column vector. I'm going to use this notation, this ket notation for psi. So psi is a column vector, and that represents a complete knowledge of a quantum system, which is, we will call a pure state of a quantum system. So psi is unit norm. So psi is 1, where this psi bra is a row vector, which is the complex conjugate of psi column vector. If psi lives in a 2-dimensional space, say 0 and 1 are one of 2 orthogonal vectors, then psi is a qubit. It's just a name given to a quantum system that lives in 2 dimensions. So psi is just any vector between in the span of 0 and 1. So alpha and beta are just 2 very complex numbers whose magnitude squares add up to 1. Okay, so psi is just a column vector, alpha and beta. Now I can define or write psi in any rotated basis. So I can define plus and minus to be 0 plus or 0 plus 1 and 0 minus 1 over root 2, and write psi in this any other basis I want. Okay, so with that being a pure state, let's talk about measuring a quantum system. So a measurement in quantum mechanics is described by a set of projectors. Okay, so these pi's, they are projectors which are defined by pi 1, pi 2 up to some number pi k, and k, the total number of projectors is the total number of possible outcomes you are allowed to get. They are projectors, so their squares are themselves, and they add up to the identity in the space where my state lives that I'm trying to measure. Okay. When I make a projective measurement, if say I measure my state psi, then the post-measurement state is probabilistic. So every time I make a measurement on the state, my state collapses to one of these states given by basically projecting the state being measured by pi k. And this is the result that I get with probability p sub k, where p sub k is psi pi k psi. And this square root of p sub k is just to renormalize the state back to being a unit norm vector. Okay? So the simplest example of a projective measurement is simply take set an orthonormal basis in the space where your state lives and construct a set of projective measurements, vectors, projectors by just taking the outer products of W with itself. So WKs, these are orthonormal bases, so WK, WJ is delta KJ, and write projectors as WK, WK. So now if I make a projective measurement with this set of projectors on my state psi, my post-measurement state will be simply WK, because I'll be projecting psi onto that WK, WK. And my probability of getting that outcome will be the inner product of psi and WK magnitude square. So a very simple example, take that single qubit. So I can construct a von Neumann measurement. A von Neumann measurement is a special case of this kind, where I make a measurement using a set of orthonormal bases and constructing projectors by their outer products. 0, 0, and 1, 1 are the projectors corresponding to, let's say, a measurement, which is what we will do on this state psi. The post-measurement results are 0 or 1, and the probabilities of the outcomes are mod alpha square and mod beta square. Now, I could do the same in another basis. So for instance, I could do a projective measurement in the plus minus basis. In this case, again, as a result of the measurement, my state is going to collapse to either the plus state or the minus state, but this time these two outcomes will happen with probability magnitude gamma square and magnitude delta square respectively. Okay, so depending upon how I rotate my measurement, the measurement results will change. Measurement results will change and the outcome probabilities will change. If I have two quantum systems, say psi A and psi B, I'm writing here two qubits. Both of them are in some state alpha beta, and this one is in a state gamma delta, so they are both column vectors. The way I write down the state of two qubits is in this form, where 1, 1 just means a tensor product of one in a state in one qubit and one state of the other qubit. And this tensor product can be thought of as a state where one qubit is in state 1 and the second qubit is in this other state 1. So this state, for example, this is a product state where my state of qubit A is in this state and my state of qubit B is that state. The most general two qubit state is any state of this form where 0, 0, 0, 1, 1, 0, 1, 1 are the four orthonormal bases of this two qubit Hilbert space. And these four complex numbers, their magnitude squares add up to 1. So clearly, I can write down states of the form that cannot be decomposed into two single qubit states. I cannot, for instance, take this state and write it down as a product of two single qubit states. So such states are called entangled states. Okay? And this particular entangled state is a very interesting one, and we'll be using that as we go forward. This is called the EPR state, or sometimes even the Bell state, the Einstein-Podolsky-Rosen state. It's a very simple to write down state, 0, 0 plus 1, 1 over root 2. Now, this is the Bell state that we just saw. And we just said that this 0, 0, 0, 1, 1, 0, 1, 1, these four are just four unit norm vectors that are orthogonal to each other, which form the basis of this two qubit Hilbert space, a four-dimensional space. Now, if I were to take this Bell state, which is also a legitimate vector in this four-dimensional space, and I do complete that basis using these vectors, each one of these is an entangled state of a very similar form, but these four are also orthogonal to each other. So this particular measurement, or it's called the Bell basis measurement or the EPR measurement, and this again has a lot of interesting effects that are at the core of a lot of quantum information processing. In particular, one very interesting thing that happens with this Bell measurement is if I take, say, two qubits A and B that are in a Bell state, and another two qubits C and D which are in a Bell state, but they are in a product state between themselves. So Bell state and Bell state. And I take this qubit and this qubit, the B and the C qubit, and I do a Bell basis measurement on these two. Okay, so it's a Bell basis measurement has 1 out of 4 outcomes, right? So 0, 0, 0, 1, 1, 0, and 1, 1, because it's a 2 qubit measurement. Depending upon which one of those 4 outcomes come about as a result of this measurement, my qubits that I did not measure, they appear in one of these 4 Bell states that I had shown before. So what we have done is that converted 2 Bell states into a longer Bell state between 2 unmeasured qubits. So there are this this particular protocol called the entanglement swap is at the heart of quantum repeaters, which are used for, or which are proposed to be used for long distance entanglement distribution. Okay, so let's talk a little bit about mixed states. So we talked about a pure state. A pure state, instead of writing just a vector for the pure state, I could take the vector, the column vector, and multiply that by the complex conjugate row vector. So this is a unit rank matrix, and this particular matrix is called the density operator of that pure state. Now in general, if I don't have full knowledge of a quantum system, it is in a mixed state. And a mixed state can be thought of as a classical statistical mixture of pure states. So a mixed state is represented by a density operator. So rho x is a mixed state of system x, which is in a classical mixture of pure states psi sub x. So psi sub x here, they don't need to be orthogonal. They are just some set of pure states. Okay, and p of x is just a probability distribution that adds up to 1 as it should. Now, the density operator defined this way has to have two things. So first of all, it has to be a unit trace. Okay, because psi's, they are unit norm vectors, and this is a probability distribution. So it has to be unit trace, and it's a positive operator. So it has a spectral decomposition. So you can take rho and write it down in terms of its eigenvalues and eigenvectors. And these eigenvalues will add up to 1. So this is the unit trace part. And the eigenvectors, they are orthogonal to each other. Now, even though I did just tell you that a density operator is a mixture of pure states, I would take that interpretation with a pinch of salt, because I can give you a density operator and write it down as a mixture of a set of pure states and another mixture of another set of pure states, and you could come up with examples like that. So, but those two density operators are not, they are not indistinct, they are the same. So density operator, indeed, that operator is the full description of that quantum system. But you can think of the density operator as a mixture of pure states, okay? Now, transforming quantum systems, the most general transformation of a quantum system is a unitary transformation. So I take a quantum system A to a quantum system B. Rho B is U, rho A, U dagger, where U is a unitary matrix. Now, if rho A is in a pure state, then this just becomes the output is also a pure state, which is just U applied on the pure state psi. But if it is a density operator, a mixed state, then this is the most general form of the output. Now, if you don't have access to a part of a unitary transformation, meaning you have a quantum system A, and this is some environment system E, and there's a quantum system, there's a unitary evolution that is happening not just on the system that you have, but on the system and the environment, okay? That is called a quantum channel. So that's the most general form of a quantum transformation we will see. Because when I have a unitary transformation, that just means that I have a closed quantum system, meaning all the evolution is happening on the quantum system I'm holding in my lab. Whereas a quantum channel in general could be a transformation on not only your quantum system of interest, but along with it some environment system which you don't have access to. So it's still a unitary on the full system, but then you trace out one of the quantum systems at the output, and that is your state that you have at the receiver. And when you write down the action of this whole thing as just between the input state rho A and the output state rho B, this map N is a quantum channel which happens to be a completely positive trace preserving map. And I'm not going to go into the definitions of that, but we'll see examples of this. Okay, so now let's start talking about some operational meanings with the quantities we have introduced, and start talking about one application in a couple of slides. Okay, so the first thing is the notion of entropy. So now if I give you a density operator rho, its von Neumann entropy is defined by negative trace of rho log rho. It's fairly simple to derive. If you put rho here as its spectral decomposition in terms of its eigenvalues lambda I and the eigenvectors lambda I inside a ket, you should be able to derive that the von Neumann entropy is simply the Shannon entropy of its eigenvalues. So it's very straightforward to derive that. What is the meaning of von Neumann entropy? So if I have n copies of a density operator rho, okay, so think of that picture we had drawn at the very beginning when we were talking about source compression. So I give you n copies of the same density operator rho, and now you have a register that is built out of with a certain number of qubits. So each of those blocks inside your memory register can hold one qubit, and the qubit can be anything. It's some 0 alpha 0 plus beta 1. So what von Neumann entropy tells you is that n times s of rho is the number of qubits you can compress it down to. And this box over here is a quantum data compression, so that's a unitary. And this is exactly true only in the limit that n goes to infinity, in the sense that the state of these n s of rho qubits can be exactly recover the original state rho tensor n in the limit that n is very high. So we need epsilons and deltas to make this precise, but this is called the Schumacher compression theorem. There is a complementary interpretation of the entropy where you are presented not with density operators rho, but many copies of an entangled state, psi AB. So say two parties, Alice and Bob, they work hard to create many copies of an identical entangled state. So every time they try, they get a psi AB state. So they have n copies of this psi AB, and then they do entanglement concentration on those states psi AB, which involves local quantum operations at their end and classical communications between A and B. And you can reduce this down to n times s of rho A number of EPR pairs. Remember, the EPR pair was the 0, 0 plus 1, 1 over root 2. So that particular entangled state, that Bell state, has one E bit of entanglement. So E bit is a measure of entanglement, again, which I will not define any more than saying that this is how we should think of E bit as a measure, that the entropy of rho A, which is, by the way, same as the entropy of rho B, because psi, a pure state, has 0 entropy. But if I trace out rho A or B, I'll get rho A or rho B, both of which will have the same entropy. And n times that many E bits is what you can extract out of n copies of psi. Okay? The most general form of quantum measurement is defined by what are called projective, positive operator valued measure operators, POVM operators. So we already saw the projectors being the defining projective measurements. So POVMs are a little bit more general than that. So they are a set of Hermitian operators that are positive or non-negative, and they are complete, they add up to identity. If I present rho to a measurement device described by a set of POVM operators pi j, I will get the jth outcome with probability trace of rho times pi j. Okay, so with that, we are ready to talk about the first application, state discrimination. So state discrimination lies at the heart of all applications in communications and sensing. So let's consider the simplest case. We are presented with one of m pure states. And say we have certain priors associated with these states. So I'm going to give you exactly one of those states, and your job is to choose a measurement such that you are able to tell me which state I gave you with the minimum average probability of error. Now, what will you do? You will pick a measurement. So a few facts to start with. I'm not going to prove that. If all of these states are orthogonal, it is pretty straightforward to see that you can get an error probability of 0. Right? How would you get the error probability of 0? We just talked about a von Neumann measurement being a special case of a projective measurement where you construct projectors out of basis elements. So we will simply construct a measurement out of the states that I gave you. So your measurement vectors, projectors are simply psi k, and you will get 0 probability of error with that, because if I give you psi k, you will get that answer, kth answer, with probability 1. Okay, now, what if they are not orthogonal is obviously the interesting case. So let's take one simple example here. This is an obvious example. So a single qubit, 0 or 1. So let's say I give you 0 or 1. If you pick 0, 0 and 1, 1 as your projectors, you will get error probability of 0, which is basically the two-dimensional example of this example that I gave you. What if you picked your measurement as the plus minus vectors? If I pick my measurement vectors to be this 45-degree rotated basis, then no matter which state you get, 0 or 1, you will always get a completely random outcome, plus or minus, because they will both happen with equal probabilities. Your error probability will be 1/2. Okay, so this is a completely useless measurement. So you will always get the same or completely garbage outcome. So let's look at the case of binary state discrimination. So I give you just two states, psi 1 and psi 2. And as you can tell that if I give you two states, all I need to give you in order to prescribe the geometry of those two states is the angle between them. So psi 1, psi 2 inner product is the sigma. So I'm going to give you sigma. And so these two states, you can think of them as lying on some plane. and you are to construct a measurement that minimizes the error probability. Okay? So you can think of your job as taking a set of two vectors that you will use to construct your measurement basis and positioning those two vectors with respect to these states that I have given you. Okay? So now if you think about it, if I take two vectors that are orthogonal to each other and align one vector with my psi 1, then the other vector will have to be at 90 degrees to that, right? So what will happen is that if I do that, if I'm presented with psi 1, I will never make an error. But if I'm presented with psi 2, I will make an error with some probability which will be given by the inner product between my measurement vector and that state. So what is the one that will minimize the average error probability? So let's first put some x-axis and y-axis here. So I'm just going to, for convenience, put an x-axis at exactly the midpoint of psi 1 and psi 2. So I'm going to call that 0. I'm just naming it 0, which is 1, 0. And the y-axis is 0, 1. So this is a unit norm vector in this direction. So these are the unit vectors. Now in this basis, it is pretty simple to see that I can write psi 1 and psi 2 like that. Okay, sigma is the inner product between them. So if I take an inner product between these two, I'll get sigma. So it's a single scalar parameter. Okay, so now consider the measurement given by the vectors W1 and W2. So W1, by the way, is the same vector that I called plus a few slides back. So it's 0 plus 1 over root 2. So it's 1, 1, and W2 is minus 1, 1 minus 1. The reason I'm calling it W1 and W2 is because I want to associate W1 with psi 1 and associate W2 with psi 2. Meaning when I get my W1 outcome, I'll say you gave me psi 1. When I get the W2 outcome, I'll say you get psi 2. So what's the error probability? So the average error probability here now is probability that I gave you psi 1. Let's take equal priors, so 1/2, times the probability that you guessed psi 2 given that psi 1 was sent. So this is the magnitude squared of the inner product between psi 1 and W2, and the other term is exactly symmetric, which is the magnitude squared of W1 and psi 2. And when you write it out, and I'm going to leave this as an exercise, it's a simple calculation. Just put these things over here, you will get an expression for error probability that will look like this. And you can forget about that magnitude here because I took sigma to be real. So 1/2, 1 minus square root of 1 minus sigma square. Okay. Now this was pretty simple, right? What if I gave you 3 states instead of 2? So now you'll have 3 states, and if I have 3 states, I'll have to give you all the 3 inner products between them in order to give you the full geometry. And now your job is to put 3 orthogonal vectors, orient them with respect to these 3 states in the most optimal way. And when I say optimal, I'm saying minimize the average error probability. So that problem doesn't sound so nice, but this was solved by UN, Kennedy, and Lax. Oh, by the way, this measurement is the one that happens to be the one that minimizes the error probability. I'm not proving it, but it's pretty easy to convince yourself that, first of all, you don't want your measurement vectors to be outside the plane, and that if you have 2 measurement outcomes that you are forced to make a decision between 1 or 2, that your measurement vector should equally straddle the states. Okay, but the proof is quite simple. UN, Kennedy, and Lax, they proved the conditions for the general case, and I'm going to state this without proof, but we'll be using that in some applications in communications and optical communications. So let's just look at what the result is and see if I can understand the notation here. So this is my ensemble that I've been given. Pi are the priors, psi I are the states, and this time I'm going to give you all the pairwise inner products, psi I, psi j. Okay? So not just 2 states, you have m states, so you have all these m choose 2 inner products. The first thing they proved is that the measurement that minimizes or achieves the minimum probability of error, or MPE, is a projective measurement. So that's not trivial. So it's a projective measurement, meaning a measurement constructed out of vectors, unit norm vectors that are orthogonal to each other, is indeed one that achieves minimum probability of error. So the picture I just gave you of positioning x, y, z axis with respect to your 3 states is indeed the right picture. Okay? So now, if you remember in the previous slide when we wrote down the error probabilities, we wrote it down in terms of the inner products between the measurement vectors and the state vectors, right? So your job of positioning the measurement vectors with respect to the state constellation can be cast as finding all of these inner products between the measurement vectors and all the state vectors. So I'm going to define a matrix. So I'm going to say that X is a matrix whose ijth element is the inner product between the jth state and the ith measurement vector. So what UN, Kennedy, and Lax showed is that if these two conditions are satisfied, then the measurement vectors will minimize the average error probability. And there are m times m plus 1 over 2 nonlinear simultaneous equations. If you can solve for these, get the x sub ij's, the error probability will be 1 minus the average success probability. And the average success probability is the probability I gave you the ith state times the conditional probability that if the ith state was given, that you choose the ith measurement outcome. So xii magnitude squared. And this third condition is just a consistency condition. You have to check this condition holds for uniqueness of the solution. But these are the YKL conditions for attaining minimum error probability between multiple states. This is sometimes referred to in the literature as the Hellstrom measurement or the Hellstrom bound. I'm not a particular fan of this because it was UN, Kennedy, and Lax who discovered it, but Hellstrom, in his book, he did a lot of very good work with this measurement, and he found lots of interesting properties of these for particular geometries of states and so forth. But just wanted to put that term here because you will probably see that term in textbooks. So let's take the simplest communication example that we can construct out of what we have learned so far. Okay? So let's say you have a binary input, binary output channel, and your channel is such that you are allowed to send 1 or 2, a classical input at the input. At the output of the channel, you get one of 2 quantum states, pure states, psi 1 or psi 2. And let's say that psi 1 and psi 2 have an inner product of sigma. Okay? So what's the most obvious thing you would think of doing? You would probably want to choose a measurement that minimizes the error probability between psi 1 and psi 2 at your receiver, right? And we just saw what that measurement will do. That measurement is simply going to induce a binary symmetric channel with a crossover probability given by that expression, because we just derived that expression to be the error probability for the binary case. Okay? So depending upon sigma, you will have an error probability of choosing between psi 1 and psi 2. So this is your minimum probability of error measurement. And every use of the channel, you send an x and the output will be a y. So if you think of the quantum channel and the measurement as one big Shannon channel P of I given x, it's just a binary symmetric channel. And its capacity is given by 1 minus the binary entropy of P. Okay, so that sounds good. So let's now do something a little bit more fancy. Okay, so let's take 2 uses of the quantum channel. And I'm going to throw out one of 2 possible outcomes, meaning I will never use that particular outcome. So I'm going to use psi 1, psi 1, psi 1, psi 2, and psi 2, psi 1. So I'm not using psi 2, psi 2. So what I'm doing is that think of 2 uses of that quantum channel, and I'm going to use 2 uses of that quantum channel so that at the output, I only produce these 3 of the 4 possible outputs. So now I'm thinking of my input as some other x. This is not this x. So every time I send a 1, I actually send a 1, 1. I send a 2, I send a 1, 2 through the channel, and 3, I send a 2, 1, okay? Now, these 3 are pure states, and what are the inner products between these 3 pure states? So the inner product between C1 and C2 is, the inner product between psi 1 and psi 1 is 1, inner product between psi 1 and psi 2 is sigma, so the inner product between C1 and C2 is sigma. Inner product between C2 and C3 is sigma square, because there are psi 1, psi 2, and psi 2, psi 1. They will give you 2 sigmas. And the inner product between C3 and C1 is sigma. So you have an isosceles geometry. Okay? So you have a situation that looks kind of like this. So your orange lines, these are your states. So this one is your is C1, and this is C2 and C3. Now we want to position a measurement geometry, my W1, W2, and W3. And it just so happens that the measurement geometry, the best thing to do is to position your measurement in a symmetric way with respect to your states. This is analogous to positioning your 2 measurement vectors with respect to your 2 states that I just talked about. I'm not proving this is optimal. I'm just asserting that this is optimal. But if I do that, then if you look at my X matrix, which is the inner product between the states and the measurement vectors, I'm demanding the same symmetry as the state has. So if you look at here, I'm saying that the angle between this blue line and this orange line, okay, which is what? So this is my C2 and this is C3. So the 2, 3 element is the same as the angle between this orange line and this blue line, which is the 3, 2 element. Okay, so I'm demanding that same geometry in my measurement matrix. So I have now 4 unknown parameters. A, B, C, D are 4 unknown parameters over here. So what I'm going to do now is to assign prior probabilities to my 3 inputs, P, P, and 1 minus 2P. The reason I'm giving 1 minus 2P to one of these because one of them is asymmetric with respect to the other two. Okay, so I'm giving P to 2 of them and 1 minus 2P to the other. And then you calculate the mutual information between X and Y. So now your X has 3 inputs, Y has 3 inputs, 3 outputs. So you have a super channel that you have induced by this inner code over 2 uses of the quantum channel. That channel has a Shannon capacity. I need to divide that by 2 because I want bits per use of my original channel. So I don't want to cheat. So divide that by 2 and maximize over the prior probability P. This time what you get is a number that can be bigger than C1. Okay? And in the limit, when these two states come very close together, meaning sigma is very, very close to 1, your R2 is 1.028 times C1. This was an example that was proven in this 98 paper by Sasaki and co-authors. So this is interesting, right? So what we have just shown you is that just blindly picking the measurement that minimizes the error probability of choosing between the possible things that the channel can spit out is not the most effective thing to do if you are trying to communicate information on that channel. Okay? And all of these standard receivers, be it optical communications, RF communications, all of them are C1 type measurements. The transduction part, the detection part acts on every channel symbol one at a time. Okay, you can do any amount of post-processing, soft information decoding, adaptive processing, any of that, but the moment you transduce, moment you detect one channel symbol and convert it to the electrical domain, you are done. You cannot go beyond C1. So what this example just showed us, although this is just a 2.8% increase, that it's a fundamental effect. This is what is called superadditive capacity or superadditive communication capacity, that by collectively measuring multiple channel symbols, the per channel use capacity you can get is higher. Okay? Now, the question I might ask you, what is, you notice that I wrote R2 over here, not C2. The reason I wrote R2 is that I don't know if this is the best 2 symbol measurement. And not yet. I mean, if you can prove it, this would be, I would say, a physical review letter worthy paper, even though it sounds like such a simple problem. And I can just give you a very brief intuition to this. When we gave ourselves the task of minimizing the error probability of choosing between 3 things, I was telling you to choose between those 3 things. So your measurement outcome can only have 3 outcome possibilities, right? So 1 for 1, 2 for 2, and the 3 for 3. But when I'm asking you to construct a measurement that has a best Shannon capacity, there was no reason why my output had to have 1, 2, and 3. My output could be a 4 element or a 5 element output, right? And it turns out that in the most general case, if I give you m pure states, then the number of measurement outcomes you need in order to maximize the Shannon information between that input and the output is m times m plus 1 over 2. This was proved by Peter Shor in a 2000 paper. Okay, so in this case, with a 3 element input, my output, in the most general case, this measurement should have been a POVM with 6 measurement outcomes. So I don't even know if a projective measurement is optimal. In fact, it's not optimal in the most general case. So you may need to consider up to a 6 element POVM. But that should be, I think, a doable task for at least for this simple problem. So C2 as a function of sigma is not known. So C2 is hard to calculate, but C1 was easy. About asking the question that what if I wanted to calculate the fundamental limit of capacity, C infinity, okay? Meaning my measurement can act across a long block of symbols, okay? I want to get what is my per use capacity. Interestingly, C infinity is also as simple, in fact simpler to calculate than C1. But C2 was this hard to calculate, and C3, C4, none of this is known. But C infinity is given by this very simple formula, and this was one of the contributions of Holevo, and this is what I'm describing you now is the Holevo capacity for a 2-input channel. So it is the von Neumann entropy of the average density operator. So P is the prior, psi and psi1 and psi2 are the 2 outputs, and it is simply that formula. So von Neumann entropy of psi1 plus 1 minus P psi2, psi2. And by the way, we just wrote psi1 and psi2 in terms of those column vectors, if you remember a couple of slides back, in terms of sigma. So you can substitute those, write down this whole matrix, calculate its eigenvalues, you will get this plus or minus, these are the 2 eigenvalues, which have to add up to 1 obviously, because it's a, this whole thing inside the bracket is a proper density operator. And the von Neumann entropy of that is the Shannon entropy, or binary entropy of that function, so which comes out to this when P is 1/2. And P 1/2 is indeed what maximizes this quantity. So this is the C infinity. Now, if you plot this C infinity as a function of sigma, sigma is an inner product, so it has to be between 0 and 1. This is C1 and that's C infinity. So we don't know if these are strict inequalities, if C2 is strictly bigger than 1 or not. Obviously, C1 is smaller than C infinity strictly. And interestingly, the ratio between C infinity and C1 in the limit that sigma goes to 1 over here, this ratio goes to infinity. Okay, so there's an infinite separation between C infinity and C1 in terms of ratio. And when we talk about optical communications in our third part, you will see that it is this regime where the states are the least distinguishable. Psi1 and psi2 inner product is close to 1 meter, they are very close together. And that turns out to be the low photon number regime for optical communication. So it is in that regime where the ratio between these two is infinity. Okay, so now that we have learned all the notation and seen the Holevo capacity, so notice that I haven't yet told you how to build a receiver to get C infinity. I told you how to calculate C infinity. But in the Holevo-Schumacher-Westmoreland proof, they give you a mathematical description of the measurement that you need to do in order to attain that capacity. It's just that translating that mathematical description to anything physical is extremely hard, and we don't know that yet. And I'll describe these physical connections in the third part of my talk today. So let's look at the most general setting. I have an input x. So this is modulation. I'm modulating x with states rho sub a of x. Feeding that rho sub a of x into my quantum channel, and I defined a quantum channel towards the beginning of my talk. It's a completely positive trace preserving map between system A to system B. I get state rho bx, I present that with a measurement, and then I get a y. The way I have drawn it here, it appears that the measurement is acting on every channel symbol. And if I take it to be that way, then I will get a p of y given x induced between this and x and this y. And at that point, you can use all of Shannon theory tools, get the capacity, and you can maximize the capacity over the choice of your priors and the choice of your measurement. Okay? And that capacity I'm going to call C11. Why 11? These through subscripts. The first subscript means that I'm sending a product state at my input. Every channel use, I'm sending a row, one of the row AXs I have in a bag that I'm picking with some probability P of X. And the second one describes that my measurement is detecting or transducing every single output, rho bx, converting that to an output y. Now, in analogy, I can define a C2, 3, C1, 2, and so forth. But the Holevo capacity of a quantum channel is defined by this formula. This is the von Neumann entropy of the average state at the output. So this is P of x rho bx minus the average of the von Neumann entropy of these states at the output. And notice that in writing that formula, I didn't tell you what pi y was, what measurement I was using. So you can calculate the von Neumann entropy, the Holevo information of this channel without even talking about the quantum measurement that you are making. And if I want to calculate C1 infinity, which is what I had shown you in the previous slide for 2 states, I'll be taking a supremum over all my possible input states, okay, and prior probabilities, but see, I don't have to talk about the measurement. So this supremum of this quantity over product state inputs and the priors, which this will give me C1 infinity. And I can apply the same formula for C1 infinity, but on the n-use quantum channel. But this time, this n-use quantum channel its inputs can span n inputs of that original channel. So automatically the inputs I'm now optimizing over for the numerator are entangled states over at the input of the original channel, which we did not do in the two-state example that I gave you. So this was actually an open problem for a long time until Matt Hastings settled this in 2009, whether there are quantum channels for which entangled states at the input give you a fundamentally higher capacity. And it turns out there are some construed examples that you can write down where you can get an improvement by using entangled states. Note that the example that I just gave you with two states, what I showed you was that C1 infinity was bigger than C11. So I was still using pure states, but I used a collective measurement at the output in order to get a higher capacity. Okay, so I think this is I would say a natural stopping point, or at least the way I had planned before I knew that the coffee breaks were going to be at the 1.5 hour mark. So it's up to this audience. What should we do? So this is where we end the discussion on general quantum information theory and application to state discrimination. Now I'm going to spend another 50 minutes or so on optical detection theory, not talk about communication yet, and in the third part we'll put these two together and talk about optical communications. So just a couple of things that came up during the coffee break we were just discussing. So I just wanted to remind everybody that in this tutorial we are going to ignore the entangled state input part. We are only going to work with product state inputs, because for optical communications over lossy, noisy channels, we don't have to worry about entangled state inputs. We showed you this two-state example where I could get a higher capacity per use of the quantum channel by picking this joint measurement that spans over two channel symbols. But the problem of how the capacity grows between C1 and C infinity as you increase the number of channel uses over which the measurement is done, that is not understood. And even C2 is not known in closed form. Okay. So this is where we were, and I just told you that the Holevo capacity, which is C1 infinity, which is what we are going to work with, can be calculated over just the one use quantum state at the output of the channel. We don't have to worry about the measurement part being collective over many channel uses. So that's very, very convenient, and that's why we were able to get that nice formula for the two-state case. So even though there is an infinity sitting over here, there is no appearance of the measurement that happens here. But in principle, if I were to search over all measurements and find the optimal one and write down the mutual information between the channel induced between the input code words and the output, its mutual information will go to that Holevo capacity. All right, so with that, let us start talking about optics. So this will be a complete deviation from what I was doing right now so far. And this section will have not that much quantum in it. And then when we go to the third part, I'll try to combine these two and talk about optical communications. A pulse of laser light. Okay? And again, I want to remind you that there is nothing special about the frequency being an optical frequency. It's just that a lot of the detector noise and the noise regimes we'll be talking about will be more relevant to optical frequency. So that's why I'm making reference to laser light or optics. E is the electric field. Okay, R is a spatial coordinate. Think of R as an x comma y, some coordinate along which your transverse coordinate along which you are looking at the electric field. And T is some time coordinate. So there is a spatial component and a temporal component. We are not going to talk about the spatial component too much in this talk, except for towards the very end. So we are going to just look at the temporal mode, the time domain pulse shape. And this oscillatory term, there is a center frequency omega naught, and T is time. And this phase is some constant phase offset measured with respect to some carrier phase reference. Okay. Now, if I were to write this electric field in units of square root of photons per meter squared second, so I have gotten rid of all the h bars and omegas and everything. So I have expressed that field in a way such that if you were to take the magnitude squared of the field, which will kill the phase term obviously, and integrate this over some area, some aperture area perhaps, and some time volume, which is your pulse length, you will get a number which will be your mean photon number. So that n sub s is in the units of photons. Okay. Now, once I do that with this normalization, and once we have identified which mode I am talking about, which S of t I am talking about, I can forget about the actual mode shape and talk just in terms of two numbers, the n sub s itself, the mean photon number, and that phase phi. And I can put these two together into that complex number alpha. The magnitude square of alpha is n sub s, and phi is just the argument of that complex number. Okay? So that alpha is all I need to describe the state of that laser light pulse once I have identified the mode that I am talking about. Is that clear? Okay. The next thing, and this is a very, very important thing that results in a lot of the conclusions we are going to draw today. We cannot measure that electric field. That E of RT, you can generate that or try to generate an E of RT as close to what you want to generate as you wish by designing, by generating that with a very low noise modulator, amplitude and phase modulator, for instance. But you cannot detect that exactly, meaning no matter how you choose to detect that field, your detector is going to add some noise to it. And the statistics of that noise is going to be driven by how we choose to detect that. So, and we are going to talk now about some forms of such detection and some forms of that noise, and see how that means, what that implies in terms of error probability and state discrimination. I'm going to, for now, put this alpha inside a ket vector and call it a coherent state. I'm going to define that properly a little bit later. But think of alpha inside the ket as a pure state which is completely described by that complex number alpha. All right, so now if I take a pulse S of t and do direct detection on it. Direct detection means intensity detection. So I'm just detecting the photons. So what did I say before this? That n sub s is the mean photon number in that pulse. I use the word mean because it is a mean. I cannot generate a laser light pulse with 10 photons in it. It's impossible. I can open up my laser transmitter for a certain time duration, the certain power, and I will get a mean power. And the reason it is a fundamentally it's a mean is because it's the number of photons I detect is a random variable. So what happens is that this 0 to 2, let's say, is your pulse duration. So S of t magnitude squared dt integrated over 0 to t is our mean photon number. I'm going to get a Poisson point process with rate equals to lambda t, meaning magnitude S of t square. A Poisson point process with that rate will give me on an average n clicks over the pulse duration, and the total number of detection events that I get will have a Poisson distribution with mean n. And note another thing is that this detection outcome k, the number of clicks I get, has no information about that phase. It only has information about alpha. So no matter where alpha was around this circle, my detection outcome will be the same. And notice another thing here is that the total number of clicks is a information that you obviously have from this ideal photon counter, but you have more information. You also have information about where the clicks arrived, and that's an important information that we'll be using to construct some of the novel detectors. Okay? So this is the model for an ideal direct detection or ideal photon detection. Nothing like this exists in the lab, but this is the, if you were to build the best possible photon counter that physics allows, that's the model. Even that will have to add this much noise to your being able to measure the field by direct detection. Okay. Now let's take an example where S of t is actually a square pulse. So E is the fixed value of S of t over time 0 to t, so that your rate of arrivals of the photon clicks is E square, which is a constant rate, and n is simply lambda t, and lambda is your rate of the Poisson point process, so it's E square times t. So n is the mean photon number of your coherent state, and the phase I have just drawn it such that the phase is 0. Okay. Now these are the actual click arrival events. They are a random process. It's a Poisson point process, and some nice properties of the Poisson point process is that the inter-arrival times, they are exponentially distributed, and they are independent events. Meaning once I get a click, the first click arrives at a time t tau 1, which has an exponential distribution with that same rate lambda. But after I have gotten that click, I can completely reset my thinking and the next click will again arrive at an exponentially distributed time, and that will be driven by that same probability distribution over here. And the total number of clicks I will get will have that Poisson distribution. All right, and this is just to show that phi does not matter in my detection event. But what this phi does, this phase does, is that you see this blue line, that this oscillatory line, this is my sinusoid that I was not drawing so far. So that sinusoid is going to be shifted by that phase phi if I were to change my phi, but it will not change the detection outcome of my photon counting process. Okay, so let's take a very simple example of modulation, binary phase shift keying, which I'm sure all of you have heard of in some context or the other, appears a lot in RF communications. So I'm going to take two coherent states with the same alpha, but a phase 0 and pi. So this red and blue oscillatory parts that you see, they're apart by 180 degrees. So first observation is that I cannot discriminate between these two with direct detection, right? There's no way, because if I gave you one of these two pulses and ask you to tell them apart, if you feed them into this photon counter, even if it is this ideal photon counter, they are going to give you clicks with the same exact statistics. So there is no information in the photon statistics that you will be able to use to discriminate between these two. Okay, we'll come back to this in a little bit. So let's talk a little bit about beam splitters, interference. Now, these funny cats over here, think of these as coherent states with amplitude alpha 1 and alpha 2, but I'm suppressing S of t here. So both of the inputs to the beam splitter, they are in the same exact temporal mode. They're both in the same shape. So from now on, think of whenever I write a coherent state as a square pulse of time duration 0 to capital T with a fixed height E, and E square T is your mean photon number. So I'm putting in alpha 1 and alpha 2, two complex numbers. The output beta 1 and beta 2 are two complex numbers which are a unitary, two input unitary applied to alpha 1 and alpha 2. And as you know that a 2 by 2 unitary is described in the most general way by two phases, one that is between 0 to pi by 2 and the other between 0 to pi, 0 to 2 pi, and the other between 0 to pi. And I can interpret one of these phases as this cosine theta as a square root of eta and the sine theta as square root of 1 minus eta, where eta, this number between 0 and 1, is the transmissivity of that beam splitter. That's the fraction of alpha 1 that goes through into beta 1, and 1 minus eta is the fraction of alpha 2 that goes into beta 1. So this is just a mixer. Okay? This is a very simple thing. You can build this in the lab. A beam splitter looks like a little cube about this big, and there's a plane that you can actually see. If you put in two laser light pulses, they interfere and they come out in two sides that you can measure. And this is, you can easily see that you can create constructive and destructive interference pretty easily. If I put alpha and minus alpha, I'm going to get no light in this output and all my light is going to come out at this output. So that's very simple to see from this equation. I can set, if I set eta to 0, then I have created a mirror for myself. All the light is coming from this way, it is going up. All the light that's coming from bottom is going this way. So it's a perfect mirror. And I can still have a phase. So beta e to the I phi. So beta goes to b to the I phi. So this is what I'm calling a pure phase. Another interesting use of a beam splitter is to do nulling. Okay, so what I mean by nulling is I want to move alpha to alpha plus beta. How do I do that using a beam splitter? So what I can do is that I put in alpha into one port, and over here I put a coherent state with amplitude beta over square root of 1 minus eta, where eta is the transmissivity of that beam splitter. Okay. If you put this into this formula over here and set phi to 0, what will you get? Your beta 1 is square root of eta times alpha 1 plus square root of 1 minus eta times alpha 2. So alpha 2 is this. So this multiplied by the square root of 1 minus eta, the square root of 1 minus eta will cancel out. I'm going to get a beta here. And this eta is very, very close to 1. I will choose it to be very, very close to 1 such that my output here will be, this will be alpha. So I'm going to get something very close to alpha plus beta, but my beam splitter transmissivity has to be very close to 1. And if it is very close to 1, this input over here has to be very large, because the 1 is in the denominator. So 1 minus so 0.999, this will make it very large. But this is something you can do in the lab, and I'll talk about an experiment where we actually did this in the lab to do nulling. So what we have done is taken alpha to alpha plus beta. In the notation of quantum mechanics, I'll talk about only briefly later, this is called the displacement operation. But what I just showed you, even though I showed you how it works for when you put in a coherent state input, this module, forget about the input, this whole module over here with a strong coherent state local oscillator with eta close to 1 will implement the displacement operator no matter what quantum state you put in. That is harder to show, but you're going to take my word for it for now. Okay, next topic. So we now know what a beam splitter is. Let's put two of them together with two pure phases. So I take alpha 1 and alpha 2. This is a 50-50 beam splitter and a 50-50 beam splitter. There's a pure phase here, pure phase here. I'm going to leave this as an exercise, very simple one. You can plug in from the previous slide the formulas. What you will see is that you can use these two 50-50 beam splitters and two phases to do an arbitrary beam splitter between the two inputs. What have I done here is that I have taken away any variability in the transmissivity of the beam splitter. I have put the transmissivity into the phase. So everything can be done by just pure phase. So if I give you 50-50 beam splitters, that's all you need to implement an arbitrary beam splitter if you have pure phase. This particular setup is also called the Mach-Zehnder interferometer, the MZI, and this appears a lot in classical optics. Now, the next obvious question to ask is that, well, what if I were to stack beam splitters together? So let's say I use this notation for a Mach-Zehnder interferometer. So this notation over here with a cross, it means that inside this I have two pure phases and two 50-50 beam splitters, transmissivity 1/2. There was a result that was proven by Reck and Zeilinger and a couple of others, 94. They showed that you can realize an arbitrary n input, n output unitary transformation. And note that this unitary transformation is a unitary matrix operating on a column vector of alphas, a column vector of complex numbers. So it's a complex valued unitary matrix that is taking a column of alphas to a column of betas, the output. It can be implemented by n times n minus 1/2 Mach-Zehnder interferometers. And in a recent work from Ian Walmsley's group, they showed a better design, better in the sense of it looks more compact and it has a rectangular form rather than this triangular form in this 2016 paper. But that one also requires the same number of Mach-Zehders. Question. Okay, that's a very good question. So the question was is the value of m, the number of Mach-Zehders you need to implement this unitary, is that the worst case? The answer is absolutely yes, that is the worst case. And I will show you an example in this part of the lecture where m is only n log n, not n square, for a special class of Hadamard unitaries. So in general, you may be able to do it with a fewer values of Mach-Zehders. Okay. Let's keep going, and this is our first problem that we will solve, okay? On-off keying and detecting between sending nothing versus sending a pulse. It's a very simple problem, okay? So I'm going to give you a promise that from 0 to time t, I'm going to either give you nothing, you'll have vacuum, or I'll give you a pulse whose pulse shape and mean photon number are both something I'm going to tell you in advance. So you know exactly that the pulse has a square shape, and this is the coherent state alpha. I'm just writing E0 as the constant field, which is square of that is your rate of the arrival process, and mod square of alpha is your mean photon number. Okay. So in one case, your mean photon number is 0. You're not going to see any photons. In the other case, you are going to see photons with that click probability. So what's the most obvious thing to do is to just put this into a detector, right, into a photon counter. And the maximum likelihood rule says that if I get a click, at least one click, it has to have come from this hypothesis. Okay, so because there is no way you could have gotten a click from this hypothesis. Let's give ourselves equal priors for both of these. And the error probability is now the probability that I got the first hypothesis times I made an error, plus the probability that I got the second hypothesis times the probability I made an error. All right, so anybody from the audience who would like to tell me what the probabilities are here? So probability of H1 and H2 are 1/2. If hypothesis 1 was the reality, if I gave you vacuum, what is the probability that you will choose H2 is the probability that you will get more than 0 clicks. What is the probability that will happen? So I gave you nothing, and will you ever make an error? No, you will never make an error, because you will never get you will always get 0 clicks. So the probability that k is greater than 0, this term is 0. Let's do the other one. H2 is the reality. I have given you a pulse. What is the probability I will make an error? I'll make an error if I get no clicks, even though I have a pulse. So if I get k equals to 0 clicks, what is the probability of that happening? The Poisson distribution. So it's the first term of the Poisson distribution, which is e to the minus n. So my error probability is just 1/2 times e to the minus n. Okay, so that's the first term of the Poisson. So that was pretty simple. And assuming ideal receiver, very good point. And I'm going to assume today, a lot of this discussion, I'm going to assume ideal modulo the minimum amount of noise that quantum mechanics forces you to add. So this Poisson distribution is what you could not have done without. That has to be there. But you're absolutely right. In reality, you're going to have a dark click process. You'll get clicks that will appear even though there is no pulse. And you will get detector dead times, meaning after you get a click, even though I'm writing a Poisson point process, your detector after it generates a click, it will just stay dead for a certain amount of time. That's called the reset time or the dead time of the detector. Okay, I'm not including any of that here. This is completely ideal. But note one thing is that this is very important, that waiting for that first click sufficed for me to get that error probability. Okay, meaning if I started detecting my pulse from here, the moment I got my first click, I'm done. I'm already able to get that error probability. I'm not even using any of the information that is there in the remainder of that pulse. Okay. So let's do something a little bit non-trivial with this. Okay, so this idea was originated from Bob Kennedy at MIT in the 1970s, but he did not quite state this receiver this particular way, but I'll talk to you about the actual Kennedy receiver later on, but the idea was there in his 1973 paper. So what I'm going to do is so if you remember this nulling block over here, that I showed, that you can use a beam splitter to move a coherent state alpha to alpha plus beta. Let's say, so you know that I'm going to give you 0 or alpha, okay? You are going to build this beam splitter with a strong local oscillator in one port with a highly transmissive beam splitter, and you are going to move 0 to beta and alpha to alpha plus beta. So you choose beta a priori, so you don't know whether you had 0 or alpha, but you just move the entire constellation a little bit to the right. What have we done by doing that? Now, the alpha plus beta, this is now less likely not to generate 0 clicks. So you have improved your error probability when hypothesis 2, meaning alpha, was given to you. Okay, because alpha plus beta, e to the minus alpha plus beta whole square is smaller than e to the minus alpha square. But you have also hurt yourself, because now by moving 0 to beta, sometimes you are going to make a mistake, even when the first hypothesis was sent, because you are going to generate some clicks. So let us write down the error probability. So this is what will it look if you do it in an experiment. This vacuum is going to go up, and this is going to go up by a certain amount. Okay, I'm just writing the fields and the coherent state description parallelly so that you can keep following that, because I'm going to come back to the field description in the future. So let's write down the error probability. So it's very simple now. So the same exact expression that I wrote, but the probability of getting more than one click if hypothesis 1 was sent is no longer 0. This is 1 minus you get no clicks, which is e to the minus beta square, because beta is what you just translated it to. So when beta is 0, this e to the 0 is 1, and you get 1 minus 1 becomes 0. But this is e to the minus alpha plus beta square. Let's try to optimize that. It's a very simple formula. You can actually optimize that over a choice of beta. It's not possible to get a closed form, but it comes to a transcendental equation if you try to differentiate that with respect to beta. But you can solve it numerically, and if you plot it, this is what you will see. So this is the error probability for plain vanilla ideal direct detection, 1/2 e to the minus n, and this blue dashed line is this error probability with an optimal choice of beta. Okay. So no intuition to what I just said, but there is no reason why this should not happen either. We did something in the optical domain before we presented it to the detector. We knew that the detector is going to give us Poisson noise. That was prior knowledge. We knew that we had exactly 0 and alpha. That's what's prior knowledge. But with that prior knowledge, we were able to do something in the optical domain so that we helped ourselves on one error term and hurt ourselves on another error term, but they balanced out in a way such that we ended up helping ourselves overall. And the optimal choice of that beta was not 0. I haven't quite shown you the calculation of this black line here yet, but you might have already guessed this is the minimum error probability you can get between choosing between 0 and alpha. But this formula should ring a bell. We have seen something like this in the first part of the lecture today, when we were talking about discriminating two pure states. Okay? So we will come back to that picture because I haven't quite yet told you how to think of alpha as a pure state. I'm just talking in terms of this laser pulse shape. Let's continue discussion in terms of this as a laser pulse and optical detection, and I'll come back to the quantum picture in a little bit. So any questions on this part? Because now it's going to get, so we are going to build on that as we go forward. Okay, so now let's go back to our BPSK constellation, alpha minus alpha. I had said that it is not possible for you to discriminate between alpha and minus alpha with photon counting, right? Because both of them will give you the exact same statistics. But now we know we have a tool in our trick of trades that we can use to discriminate between them. Why? Because I can shift it around. I can take minus alpha and alpha to 0 and 2 alpha and then detect. That was Kennedy's idea. So this is what Kennedy had proposed in his 1972 paper. And by doing so, your error probability will be 1/2 e to the minus 4n, right? Because we saw how to discriminate between 0 and alpha, and that error probability was 1/2 e to the minus square of the on pulse amplitude. So if now your on pulse is 2 alpha, so your error probability will be 1/2 times e to the minus 4n. In a paper many years later, in 2008, Masahiro Takioka and Masahide Sasaki, they said that, well, instead of moving minus alpha and alpha to 0 and 2 alpha, why not move it to beta and 2 alpha plus beta, optimize over beta. I'm not writing the expression here, but by optimizing over the choice of beta, you can get a lower error probability than this. I'm not going to show you the expression, we'll show you the plot in a little bit. So this is not optimal nulling. So this idea of this optimized nulling to get a better error probability, this was done in that paper by Masahiro. But note a couple of things here. We gave ourselves a lot of information in order to be able to design that in the lab. Why? We need a phase reference first in order to null, because if you remember in the beam splitter, you have to have in order for you to interfere, they have to be in the same temporal mode, and you have to be exactly phase aligned. Okay? And the second thing is that we are giving ourselves the information about the amplitude reference as well. Meaning I have to know what alpha to expect to see in order to move it to beta and 2 alpha plus beta. So I'm giving myself both amplitude reference and a phase reference. Can you build a receiver that can discriminate between BPSK, alpha minus alpha, but only with a phase reference, but where amplitude reference is not required? Because amplitude reference requiring that is very artificial. You are looking at the output of the channel. You don't know how much loss is going to be there in the channel. So we don't know what is the actual amplitude you will receive. You'll probably know that you will receive some minus or plus beta, but you will not know what that beta is. Okay? So that takes us to the next receiver design we'll talk about. And again, very simple to understand from what the theory we have learned so far, called homodyne detection. So the way the homodyne detection receiver works is the following. So let's look at this pulse over here. This was our original pulse alpha. E is the constant field, T is the time duration. I'm going to mix that alpha on a 50-50 beam splitter with a very strong local oscillator. So this local oscillator is also a coherent state, but its field, alpha LO, is much larger than alpha. So magnitude squared of alpha LO, which is the mean photon number in that local oscillator pulse, is much larger than the mean photon number in the original pulse. What you will get at the output is alpha plus alpha L over square root of 2 and alpha minus alpha L over square root of 2. And we are going to now detect both of them using ideal detectors. Okay? So these two detectors are now going to generate a Poisson point process for each one of them. One will be driven by a rate function, which is the magnitude square of that. And this one is going to get a rate function, which is a magnitude squared of that. And then we'll take a difference of those two and integrate over the pulse duration. And that will be my final output Y. So let's think about this. This final output Y, this Q is the electronic charge. So if you remember in the picture of the photon counting detector that I drew, I had these delta functions at the points where the photons arrived. the click patterns. And at the top of the delta functions, I wrote Q in brackets. So Q is the area of that delta function. That's the electronic charge. So the output can be thought of as the electronic charge, because this is the photocurrent that is coming out, is that train of, that is the Poisson point process of many delta functions, each one of area Q. And K plus and K minus are two Poisson random variables with mean this and that. And G is some gain in this difference amplifier, S is perhaps some other gain you may have in that integrator, but you can ignore G and S, you can ignore even Q also for any practical purposes. So the output is simply a difference of two Poisson random variables. Two Poisson random variables, but then this alpha LO is much larger. So you can actually prove that in the limit that alpha LO is very large, this difference gets closer and closer to a Gaussian random variable. The mean and variance are very simple to calculate. The mean of y is just that is a constant times the mean of this is n plus, mean of that is n minus. The variance is just the sum of the variances times the square of that. And you can write down the mean and the variance that way. And it goes closer to Gaussian as alpha LO becomes larger. Now it's a simple exercise. Actually, we can do it right here. Let's say I scale this output y with a constant s. I choose my s to be 1 over 2qg alpha LO. So I choose my s such that mu becomes alpha, the mean. Okay? Then what will the variance be? So the variance will have to be divided by the square of that s. If you do that over here, square of that constant that we have just chosen, you will see that you'll have to make this approximation that alpha over alpha LO is very close to 0. You will get this number as 1/4. Okay, so by homodyne detection, we did not give ourselves the knowledge of alpha. We did not give ourselves the knowledge of the actual value of alpha, but we were able to design a receiver that gives us a Gaussian distributed random variable with mean alpha, but the price you pay, the kind of noise we see in this receiver is a Gaussian noise with a fixed variance of 1/4. And that 1/4 is again fundamental. That's called the short noise limit of homodyne detection. So now you saw something very interesting here, that we still at the heart of our detector, we were working with two direct detection devices. These were generating Poisson point processes. But we did something around it so that we converted the Poisson statistics to this Gaussian statistics, but something that is able to give us a measurement of alpha and minus alpha without having to know alpha. We are still playing with that same noise process. And the way that Poisson point process manifests itself in presenting it to you is this variance of that Gaussian distribution. And by the way, it is that 1/4 because of which I have been drawing those alphas as that blurry circle with the orange, the blur around it. That blur is supposed to represent that variance. And this whole thing is called a balance detector, which you can actually buy commercial off-the-shelf balance detectors from, for example, from Thor Labs. You can just buy this whole thing. You will just hook up a strong local oscillator laser and an integrator at the output. Okay, so now, second thing, this is a very simple exercise you can do yourself. Instead of taking alpha LO to be in phase with alpha, take alpha LO to be e to the j theta LO times square root of n LO. So the mean photon number is still much larger than the mean photon number of the input, but there is a phase difference between the two. Now, question? Good question. Yes, so they are, if you were to, they are independent, so the short answer is yes. Something I did not say I should have mentioned, that in the beam splitter, when you mix two coherent states, alpha and beta, you get alpha plus beta over square root of 2 and alpha minus beta over square root of 2 on the other output. If you were to detect those two, so first of all, those are two independent coherent states, meaning if you detect those two, the detection outcomes will be independent. This is not true in general. If I were to put in, for instance, a squeeze state or a number state or some other form of quantum state, then the beam splitter can produce correlated or even entangled outcomes. So they are independent random variables in this case. Okay, so now if alpha and alpha LO had a phase between them, some theta LO, then you will get the exact same outcome. Your output will still have a mean proportional to alpha, but you will have a cosine theta plus theta LO term over here. The variance is still 1/4. So you see that you are able to not only measure the mean of alpha, you are also able to measure the angle. So it's a very, very powerful measurement. So homodyne detection can get you the value of alpha and its and the phase as well. Okay, and the other thing to note here is that this is a mode selective receiver, meaning here I was talking about, I chose my local oscillator to be in that square pulse shape, the same shape as my input pulse was. But I could have chosen my local oscillator in maybe a Gaussian shape. What then it would do, and I'm not showing that here, is that it will, as if you write down your input pulse in a mode function, you write this down as a, say, expand that in the Hermite-Gauss basis, where Gaussian function is just the first term in that basis and there are other terms. Homodyne detection automatically will do the homodyne detection only on the Gaussian component of that input. So the local oscillator is doing two things. It is able to extract the mode that you are doing homodyne on and cull out everything else, and that strong local oscillator is giving you the ability to do this measurement on an any alpha with the same variance without knowing the value of alpha. Next, so think of now this homodyne detection as a black box. So alpha, so this theta LO is the local oscillator phase, and NLO is the mean NLO is the mean photon number of the local oscillator, which I'm taking to infinity. So if I now give you BPSK alpha and minus alpha, you will get a Gaussian distribution with mean at minus alpha or alpha with a variance of 1/4, and it's fairly simple to write down the error probability transition matrix. You're going to get this 1/2 arc function of square root of 2 n bar. This is the probability that if I send alpha minus alpha, that your Gaussian outcome will lie in this regime over here in the tail, so that you will guess it as alpha. So that's very simple. We have seen this formula many times in other contexts. Questions? Okay. Heterodyne detection. Very simple construct that follows homodyne detection. So let's take that input alpha and split it on a beam splitter first. So split that alpha into two parts, alpha over square root of 2 and alpha over square root of 2. Both of them are identical. But do homodyne with theta equals to 0 and 1, and do homodyne with theta equals to pi by 2 on the other. Okay. So now I will have two outputs, y1 and y2, and you can see here that this will be, the mean is now alpha over square root of 2, but the variance is 1/4. But you are measuring one phase, and here you are measuring the orthogonal phase, but your variance is 1/4. Now if I rescale the y1 and y2 by multiply that by square root of 2, what I see here is that one of the outputs, x1 is the scaled version of y1, has a mean which is equal to the real part of alpha e to the j theta LO with a variance of 1/2, and the other output is the imaginary, has a mean of the imaginary component of alpha e to the j theta LO with a variance of 1/2. Okay, so this is a very simple exercise from here to here. It's just a scaling of means and variances. But what this shows is that now I can measure both quadratures of alpha. I can measure the real and the imaginary component of alpha at the same time. The price I pay is the noise variance on my measurements is twice the variance that I had in this thing when I was measuring only one quadrature. Okay? So I can now use this to discriminate things like a QPSK constellation, like 4 constellation points, which I could not have done using BPSK. Let's do another receiver. So far we have been building receiver designs that gave us a probability of error. Okay? What if I wanted to design a receiver that never makes an error? Okay, whenever it guesses an input was sent, it always is absolutely sure that that input was sent. But sometimes it just fails. It just raises its arms and say that, I don't know. And that I don't know outcome is called the erasure outcome. So a very simple way to design such a receiver for BPSK is following. I think this was proposed also by Masahiro and some others in a paper in the early 2000s, but I don't remember the reference. So what you do is that you take your pulse here, and this input is either alpha or minus alpha. Okay, you don't know which one it is. And that's this output. But you mix that with a fixed alpha. So you give yourself the knowledge of alpha here also. Now what happens is that if alpha was sent here, all the photons will come out in this output, and if minus alpha was sent here, all the photons will come out in this output. But since this is a coherent state, you will still have a probability that this K1 or K2 will be 0, in which case you will just not know. Okay. But if you built this detector with a simple beam splitter and 2 detectors, if this detector clicks, what does that tell us? It tells us that the click has to have come from this alpha pulse, because if minus alpha was sent, then this mode will have no photons in it. So any of those detectors clicking will tell us exactly which one of the inputs was sent. But with a probability e to the minus 2n, I will not get anything. I will get an erasure outcome. So this is the transition probability matrix. I have 2 inputs but 3 outputs. 3 is the erasure output. But now if I were to force to make a hard decision, meaning I have to map this 3 output to one of these 2, and I can do no better than flipping a fair coin to do that, I'm going to spill over that e to the minus 2n half to the two of these. Okay, so I'm not going to get a measurement that has a perfect unambiguous state discrimination. This style of measurement, and I'm going to use that in the third part again, is called unambiguous state discrimination, and there is a whole theory behind this as well. Just like I talked about the UN Kennedy and Lax measurements for minimum error probability. If I gave you m pure states and asked you to write down the best possible USD measurement, meaning the one that minimizes the probability that you will get that erasure outcome, there is a very specific way of writing that, and it comes out in terms of the maximum eigenvalue of the Gram matrix, which is the matrix of pairwise inner products of these states. Okay, I'm not going to show that here, but just to set terminologies, receivers like this we are going to refer to as USD, or unambiguous state discrimination. Now some time to plot some of the results we have seen. Okay, so this is BPSK. So this pink line is the error probability achieved by the USD when it was forced to make a hard decision. So USD measurement is something you would never want to do if you want to eventually force it to make a hard decision. USD measurements will be good, as we will see, when you are designing receivers for communication where you want to leverage that erasure outcome to be taken into account by an outer code for getting better capacity. This red line is the probability of error of the homodyne. So this is your 1/2 ERFC square root of 2n. This blue line is the Kennedy receiver with the optimized value of beta. And that black line is something I haven't talked to you about. This is the optimal receiver. So that's the minimum error probability. But something to be seen here is that this optimal error probability we'll talk about in a second, but the exponents of these two sets of curves, so these two curves, they go as e to the minus 2n, whereas these two curves go as e to the minus 4n. So this was a big achievement of Kennedy, because Kennedy was the first one who wrote down a receiver construct, which was this blue line, which even though it did not attain that black line, the minimum error probability exactly, he knew how to calculate that minimum error probability. It was very simple. It was a 2-line calculation, as we saw today morning. But writing a receiver construct was very hard. He was able to get that e to the minus 4n error exponent, whereas the only receiver we know how to build, a standard receiver, is homodyne detection receiver, which will give you this factor of 2 worse error exponent. Okay, so let's take a detour and put in context so far what we have been talking about in terms of coherent states in the quantum picture. I'll again introduce as little notation as we just need to understand what we are doing, and then we'll go back to optical detection. Okay. So I talked about a mode. I showed those S of t, S of t was the square pulse. And I said that if you have a laser light pulse, then just giving you that complex number alpha was all I needed to give you to tell you the whole state of that pulse. But that's not the case in general. That same mode, S of t, it could be in some other state. For instance, that S of t, or here I'm writing that as a phi of t, some mode, a quantum system, can be in some other states. So the kinds of states we have been talking about so far are coherent states. And if we do an ideal direct detection of this mode, then we get a Poisson point process with a rate function magnitude phi t square, and the total number of photons is a Poisson random variable of mean n, where n is the integral of magnitude phi t square over the whole pulse duration. But then phi t could also be excited in a number state. And a number state is a highly non-classical state, and it's very hard to generate. So remember, I just told you a little while back that it's impossible to give you that square pulse and say that there are exactly 10 photons in it. But in principle, it is possible. You can generate a mode with a fixed number of photons in it. And you can definitely do that for single photon states, and there are many experimentalists working on that. So let's for now give ourselves this notation n to denote the quantum state of a mode with exactly n photons in it. Okay? And n goes from 0 to infinity. Now if I were to feed in now this mode into that direct detection device, I'm going to get exactly n clicks. Okay? First of all, it's very hard to produce. But the statistics of the arrival of those n clicks is no longer a Poisson point process. It cannot be, right? Because if I know there are 10 photons, and I have already gotten 3 clicks, I know I can only get 7 more photons, and I will get exactly 7 more photons, except that I don't know where they are going to appear. I'm not going to write down the arrival process statistics, but you can write it down. It's not a, it's a process with memory. It doesn't have, it's not memoryless like a coherent state. There are many other types of states that that mode could be in, and the most general state that that mode could be in, most general pure state actually, is a superposition of these number states. So you can now think of these number states as a basis, a complete orthonormal basis of the Hilbert space of a single bosonic mode. So any state like that, a superposition of n, where Cn magnitude squares add up to 1 is a legitimate state, I can excite that mode in. So you have to think of this mode is a shape of electromagnetic field, and I'm exciting that in a quantum state, and that quantum state in the most general way can be written as a superposition of number states. Of course, I can have mixed states, but I'm not writing that here. So you can think of these number states as column vectors, 0, 1, 2, and so on. These, they are orthogonal to each other. A coherent state happens to be that particular superposition of the number states. And if you can see that if I take a magnitude square of that, I'm going to get a Poisson distribution. Ideal photon detection is a von Neumann quantum measurement described by these NN projectors. We already talked this morning about what von Neumann projectors are, and photon counting, meaning counting the number of photons, is quantum mechanically described by that projector. So if I were to do ideal direct detection on a coherent state, it will give me outcome n with probability magnitude square of n overlap with alpha, which you can calculate from here, which is magnitude square of Cn, which is that. All I'm doing right now is that writing everything we saw so far in quantum notation. So this application of quantum to understand photo detection statistics of laser light pulses is a little bit of an overkill. We don't need quantum mechanics to describe this output. This completely can be described using semi-classical theory of photo detection, which is Poisson noise statistics of when you put in a laser pulse into a direct detection device. But clearly this is much more powerful because we can talk about all other classes of quantum light and their detection statistics. So Poisson detection statistics is a result of the projection of the coherent state into one of the Fock states. All right, so this should be an easy exercise. We can take that coherent state expression, alpha, and take alpha and beta to be 2 complex numbers, 2 coherent states, and write down their inner product. So we know how to do that because the inner product between Fock states is a delta function, delta mn, because these are orthogonal. So if you do the math, you will see this is the expression you will get, inner product between 2 coherent states. Now if I take alpha to be alpha and beta to be minus alpha, and I put it over here, this is real, so the star goes away, and this beta square is alpha square, so this 2 cancels out, and you are left over with e to the minus 2n. Okay, so e to the minus 2n, where n is the mean photon number of the coherent state alpha. That is the inner product between alpha and minus alpha. Now take a moment and think of all that we were talking about this morning about 2 states, psi 0 and psi 1, with the angle sigma around between them. That sigma is this e to the minus 2n. So if I increase n, if I have a higher and higher photon number, e to the minus 2n gets closer and closer to 0, which is physically meaningful, that with a higher photon number, my coherent states alpha and minus alpha are becoming easier and easier to distinguish because they are becoming orthogonal, more and more orthogonal to each other. But for any fixed alpha, any finite alpha, the 2 coherent states alpha and minus alpha cannot be distinguished with 0 error probability because they are not orthogonal. Their inner product is given by this. Now we already know what is the minimum error probability of discriminating between this. We did this exercise in the morning. We got this formula, if you remember. I'm just going to substitute sigma as e to the minus 2n. I'm going to get that formula. So Kennedy knew how to do this calculation. This is, as we saw in the morning, this was just a 2-line calculation. But writing a receiver construct that gets you this error probability was very hard. Okay, so now you can do the same thing for on-off keying, so 0 and alpha. The inner product between 0 and alpha from this formula you can calculate to be to the minus n over 2. So the error probability is written by that. And I had shown you a plot of this a few slides ago, which was below the error probability of the Kennedy, which was below the error probability of direct detection for on-off keying. Okay, so the calculation of these error probabilities were easy, but how do you build a receiver that will actually achieve this? So instead of deriving that receiver, I'm going to give you the answer, okay, and describe you how that receiver works. And then I will discuss why discriminating between two states is so special, and that already was so hard that we don't even know how to get to the quantum limit of discriminating between 3 states or more. Okay, but for 2 states, we do have an answer. This came out of a PhD thesis from MIT, Sam Dolinar, who was one of Bob Kennedy's PhD students. His whole PhD thesis, and if anybody is interested, I have a PDF of that I can share. It's about a 200-page thesis, just dedicated on finding a receiver design that attains that 2-state minimum error probability of coherent state discrimination. It's an amazing piece of work. The way the final answer is the following. So think of this is your coherent state alpha and minus alpha, and this E is the constant field, minus E is the constant field for the other one. What you do is the following. You put in the pulse into the detector, but not directly. You take the pulse, the input pulse, and you add one of these 2 waveforms to that pulse. So this is your S of t, which is being fed. And see here, I'm just writing, I have drawn E to be very small. I should have drawn it with a slightly bigger value. So, but you can see the step function, the blue step function and the red step function. The receiver starts out with a belief that the blue hypothesis or the alpha hypothesis was true. Okay, it's just an internal belief. When it believes that the blue hypothesis is true, it applies the blue feedback, the U plus t, and it adds U plus t to the input pulse here. So what actually goes into the detector is a sum of E and U plus t. Okay? So E of your pulse is a constant. It's either E or minus E. You don't know which one it is. But you start with a belief that it is the top one, the blue one. And when that belief is true, your receiver applies this feedback. So what you are sending in here is a very, very strong signal. See that U plus t becomes very high in amplitude. Both U minus t and U plus t, they are very high in amplitude when you start out. So this is 0 and this is t. So I'm just drawing it for a 10 nanosecond pulse interval. So you immediately see a click, right? Because you are sending in such a strong signal to your detector. The moment you get that click, you switch your mind and you now start believing that the red hypothesis was true. Okay? And when you start the red hypothesis being true is your belief, you start feeding in this wave function. So you toggle between applying either U plus t or U minus t into this detector. And then you keep, every time you get a click, you switch your mind about which hypothesis was true, and you switch between applying one of those 2 feedback waveforms. But this detector that sits over here, this is still generating a Poisson point process, but except that your Poisson point process, the rate of that Poisson point process is changing every time it's generating a click because it's being fed with a feedback waveform. So it's making it change the actual field that gets fed into it. When you do the math of the error probability for this with these 2 feedback functions, as I've written here, you will see that this receiver achieves that error probability. Exactly the minimum error probability that comes out from a totally different analysis, that 1-page analysis that we showed of discriminating between 2 states. But the design of this receiver had almost nothing to do with the way we calculated the minimum error probability. This was a physically driven design of a receiver that Dolinar develops in his thesis. So if you look at the actual feedback waveform, it will look something like this. So this is actually from a MATLAB simulation I did. So you will see there's a click arrives, you switch again, and you keep switching between these 2 waveforms. And if you do it many times, collect statistics, you will see that error probability. Yeah. The final guess is your current belief. It's very simple. You start with believing one of the hypotheses, keep toggling, and whichever is your final belief, you stop there. And I'll give you an intuition for that in the next slide, why that works. Okay. So let's think of this pulse as slice it up in time into many, many tiny little bins. So now we are going to start developing intuition for why the Dolinar receiver works. Okay. So this was my original pulse, 0 to t. I'm going to chop it up into k segments. So you think of this pulse being fed in a little by little. Okay. And every little piece that is being fed is a coherent state with a mean photon number alpha over square root of k, so that the total number of photons is same as n, the original coherent state. Now, what the Dolinar receiver is doing is that it is basically working with each one of these tiny little segments, but these little segments are two coherent states, two BPSK coherent states, but with very tiny amplitude, alpha over square root of k and minus alpha over square root of k. Okay, so now let us look at this carefully, because this is the intuition mainly. So this is just my way of describing it. You may have a different way of thinking about it. So I took alpha and minus alpha and I sliced it up into k slices, k independent coherent states, each of which is either alpha over square root of k or minus alpha over square root of k. So now think of this, you are starting with the first slice, what will you want to do? So if you had to just discriminate between two coherent states, BPSK, and you build the Kennedy receiver and Dolinar already knew Kennedy's receiver at the time, so was his actual way of thinking. He had told me that. So you start with alpha and minus alpha over square root of k, and you move it to the very far to the right. So your beta that we talked about, that optimal beta when alpha is small, is very high. In fact, so much so that when alpha goes to 0, the optimal beta becomes infinity. So you move these two from the center, basically from the middle over here, you move it all the way to the right. Now, when you have done that, which one of these two hypotheses is more probable to generate a click? The one that is further from the origin is the one that is more probable to generate a click, right? Okay. So what you are doing by doing the translation is that we are saying we first start with a belief that this hypothesis, H2 hypothesis, is true. This is the top one, alpha. And I'm now trying to disprove myself. I took that alpha over square root of k minus alpha square root of k, moved it so far to the right that the moment the first click comes, I know that it is more likely that it has come from hypothesis 1. So I'm sorry, I misspoke. So I started with a hypothesis that this was the minus alpha was in fact the right one. That's why I moved it to the right, because I wanted to disprove myself. The moment I got a click over here, so see I got a click here, I moved this hypothesis to the left side. So this is my nulling schedule, the red line. But whether I go to the right or the left is determined by whether I got a click. So this is the first time, so I have a H1 as the belief, which is this one, shifted to the right, didn't get a click. Next slice, I again moved it to the right, I got a click this time. So I switched my mind to hypothesis 2 being true. So I took this third slice and moved it to the left, I got a click. So I switched my mind to hypothesis 1, and I took the next slice and I moved it to the right, didn't get a click. I kept on believing hypothesis 1, and then I again moved it to the right, but I'm following my nulling schedule. But I got a click, I again shifted my hypothesis to 2, moved it to the left, and so on. This receiver, at the very end, what will happen is that hopefully you will come to a time where you have nulled it, you have moved it such that the true hypothesis in fact is what you are currently believing in, which will make you move these slices in a way that the true hypothesis will be sitting at vacuum in the middle, so that you will not get any more clicks. So that's why when you stop getting clicks towards the end, you're not getting any clicks. Your final hypothesis is what you believe at time t. It's a beautiful design of a receiver, and it's a very intuitive, but you can actually work out the nulling schedules, which is this red line, which corresponds to what I was drawing here, these two nulling schedules. These are the formulas for the actual time waveforms, which will give you the Hellstrom limit. What the Kennedy receiver was doing in this picture that I have drawn is actually something very simple. It was taking all the slices and moving all the slices so that hypothesis 1 was aligned to the middle and hypothesis 2 was over here. So the moment I got a first click, I switched my mind to hypothesis 2 and I stayed there. So I was not using these other clicks that could have arrived here, because no, I know that once I get a click, it has to have come from hypothesis 2. So Kennedy receiver was doing this, Dolinar receiver is just using a different feedback schedule. So that's how you get to this black line, this minimum error probability. Okay, so now you could use a similar strategy for multiple hypotheses. So let's say we have a QPSK constellation. You have 4 constellation points. I can chop it up into k slices, And I can do the same thing with the first slice. I can try to null hypothesis 1, meaning bring that hypothesis 1 to vacuum, and everything else just goes wherever they go. And the first time I get a click, I rule out H1, because if H1 was indeed true, this could not have generated a click because it is sitting at vacuum. And then I start nulling for the next slice onwards, I start nulling H2 and so on. And then my final hypothesis over here is my current belief. This receiver was proposed by a person called Roy Bondurant, and this is the performance of that receiver with a Kennedy-style optimized displacement is shown over here, this blue line. And this red is heterodyne detection. And what was shown is that there is a very similar error exponent improvement you get. So this scales as e to the minus n over 2, whereas this scales as e to the minus 2n. You get a factor of 4 improvement this time in the error exponent. However, the Hellstrom bound, again, is simple to calculate because we showed in the morning how to calculate the minimum error probability between any set of states. And we actually did a calculation for 3 states. So you can calculate the minimum error probability, but this time we don't know how to build a receiver that gets you to that black line. In fact, we believe that a Dolinar style receiver does not work. And this paper, although they don't prove it, a few years ago, Chris Marquardt's group, they put out this paper where they showed that they tried exactly a Dolinar style receiver for 4 PSK, optimal displacement. Instead of exactly nulling, pushing it a little bit further out, worked out the nulling schedules. It's a long and complicated paper. You can take a look. They showed that at least that strategy does not work. So we don't even have a receiver design that gets you to that Hellstrom bound. So take a ternary example, 0, alpha, and minus alpha. Okay. So for 0, alpha, and minus alpha, we can write down the Gram matrix, the pairwise inner products, which is simple. This is the inner products. It has an isosceles geometry, just like the example we saw in the morning. Because alpha and 0 have the same inner product, alpha and minus alpha have another inner product, and minus alpha and 0 have the same inner product as 0 and alpha is 0. So these two are alpha and minus alpha, and this is vacuum, the orange lines. And we position our measurement vectors W1, W2, and W3 with respect to my 3 vectors so as to minimize the error probability. And we went through the math in the morning. So we have to calculate the terms of this measurement matrix, which are the inner products between the state vectors and the measurement vectors, which boils down to finding these 5 unknown parameters A, B, C, D, and E. I just wrote down the UN, Kennedy, and Lax conditions for those 5. So I got these 5 equations, so 4 equations and 4 variables. You can solve it using the Newton's method. It's analytically, you can only go this far. And then you can plot it. So this is the error probability of discriminating between 0, alpha, and minus alpha. Which receiver would you use if you were to discriminate between those 3 from all the receivers we have talked about? One of the standard receivers. That would be homodyne detection, right? Because I have minus alpha, 0, and alpha. If I used homodyne detection, I'll get a Gaussian with the same variance 1/4 with either mean at 0, mean at minus alpha, or mean at alpha. And you can write down this error probability. You will get an arc function, square root of n bar. You can plot that. This is the error probability. And this is the quantum limit, but you can show that the quantum limit goes as e to the minus n, whereas the homodyne goes as e to the minus n over 2. So there is a factor of 2 worse. And you can design a Kennedy-like receiver, which will get you to the e to the minus n scaling. And this was work I did with my colleague Ranjit Nair a few years ago. This applies for any constellation, but it does not exactly attain the PE min. So we don't know how to get to the exact PE min. Pulse position modulation, another example of state discrimination that appears in optical communications a lot. You have m coherent states, okay, so in your code word, and you have an alpha in 1 out of these m positions. So now what does your Gram matrix look like? You have every pair of states from that constellation has the exact same inner product. It is, so if you think of 0, 0, 0, 0, 0 and alpha and 0, 0, 0, and then another 0, 0, 0 and alpha zeros everywhere else. So if you take the inner product, you will get alpha 0 times 0 alpha, and all the others will be 1. So it will be a square of the inner product between 0 and alpha. But it is an equidistant geometry. All the vectors in this m-dimensional space, they are equally, every pair has the same inner product. So the measurement matrix that minimizes the error probability also has the same exact geometry, not showing the derivation, but you can write down the minimum error probability. It is a more complex expression. If you use direct detection, the error probability is very simple to write because I will just do direct detection on every slot, where I get a click, I will say that was my alpha, that was where my alpha was. So the probability I will make an error is that your right position does not generate a click, which is e to the minus n, e to the minus alpha square. Times this m minus 1 over m is just comes from the probability that you will make an error if you were to make a random guess if you don't get a click. We built a receiver or designed a receiver, this called a conditional nulling receiver. This works in the same Kennedy-like philosophy, but on a slot by slot basis. You start applying a nulling pulse on the first one. Based on a click, you decide how much you want to null the next slot, and so on and so forth. You can write down an error probability expression which has the right exponent, meaning has e to the minus 2n exponent as opposed to e to the minus n, but does not exactly attain the error probability. Actually, the original version of this conditional nulling receiver was also in the last chapter of Dolinar's PhD thesis, it's interesting when you read that section, because he seemed to be at the, if you read the thesis, it seems like he's really struggling with that, because that was the only Emory case he tried, and he was not too proud of that section. He just wrote it, but it was a very, very nice calculation, because he was not able to get to the minimum error probability achieving receiver. But he was able to find something that gets the right exponent, and then he sort of abruptly stops. And even now, we don't know a receiver that gets you to that probability of error. In this paper with Masahiro Takioka and John Habif, we improved a little bit on that receiver probability of error performance by using squeezing, but still the quantum limit eludes us. So this is direct detection. That's Dolinar's original conditional nulling receiver, and then this was our two improvements from our paper. But they both have this right error exponent, but does not get you to the quantum limit exactly. And this was an experiment we did of that receiver in our lab at BBN. So anyway, so just take a step back and think of where we are right now. So we have talked about a variety of different types of optical detection. We talked about Poisson noise being a limiting factor, and we showed a variety of things you could do to the optical domain signal before you detected it to position it better to the detection noise that is yet to come, if you know what you're trying to do with the signal. But so far, what we have been working with is just beam splitters and photon detectors, because that's, if you remember in this section of my talk, the only two things that I had to introduce to talk about all of this was two things: interference and Poisson noise. I didn't use anything other than those two for all this development. Those two things happen to be not universal, in the sense that all optical transformations cannot be done using those two things. If you added a new thing to your toolbox, for instance squeezing, then it will become universal. So squeezing is a very interesting tool which has not yet been tried, well, it has been used. I'll talk to you about a few examples, but it would be very interesting to try to use squeezing along with direct detection to see if you can get to the quantum limit of state discrimination, which underlies all applications in communications and sensing. So just to give you a black box picture of squeezing, this is what you do. So you start with a coherent state alpha. If I apply this squeezing, which is a unitary transformation, it takes alpha and squeezes the mean to beta, which is alpha times e to the minus r, and r is the amount of squeezing you're applying. Okay. But in addition to moving it to closer to the vacuum, you see that the way I have drawn this circle now, I'm drawing it as an ellipse. The reason I'm drawing it as an ellipse is because if I do a homodyne detection along this quadrature, I'll get a variance which is 1/4 times e to the minus 2r, not 1/4. And if I did a homodyne measurement along this direction, I'll get a variance of 1/4 times e to the plus 2r. So I'm squeezing the variance in one direction and anti-squeezing the variance in the other direction. And I'm changing the mean. Okay, so this is possible to do. So your homodyne detection results in this mean and the variance. But one thing you should notice here is that this homodyne detection outcome I could have just done by classical post-processing. My homodyne detector gave me alpha comma 1/4, right? Alpha was the mean, 1/4 was the variance. I could just take that and could have multiplied that by e to the minus 2, e to the minus r, and I would get that outcome. So homodyne detection preceded by squeezing is not as powerful. On the other hand, if you look at what happens when you do direct detection or photon counting on that squeeze state, what you get is, I'm not writing the full expression for the probability of getting k clicks because that's very complicated. I'm just writing the probability that you will get no clicks. So see here, if r is 0, this term becomes 1, this tan hyperbolic becomes 0, and you retrieve the e to the minus n, the first term of the Poisson distribution. But when R is greater than 0, the squeezing amount, this is different. And what happens is this keeps increasing as you increase the amount of squeezing. So let's think for a moment about what the Kennedy receiver did. It took minus alpha and alpha to beta and 2 alpha plus beta. We were increasing the likelihood of getting a click for both hypotheses. Just that one was increasing at a faster rate than the other one, and we found the optimal place to operate. Squeezing is another toolkit to change the detection probability. And this expression that I wrote down here, the calculation of this expression I cannot show you. This is out of the scope of this tutorial, because to show you that the derivation of that, I'll need to use quantum mechanics. This is where I cannot do this with just Poisson point process and beam splitters and phase shifters. So this is a true quantum process. But it's not hard. If once I write down the squeeze state in the number basis, you just take the inner product with the number states, you will get that. But this is a physically meaningful state. You can realize that, the squeezing effect in the lab. So what Masahiro and Masahide Sasaki in that paper that I talked about, the generalized Kennedy receiver, they actually tried something interesting. So they said, instead of just applying displacement followed by photon counting, what if I applied displacement and squeezing before I did photon counting for the same BPSK signal? So he was not applying a Doliner-like feedback between detection and induced feedback. Just take the full coherence state, applied it as displacement and squeezing followed by that, and then detected it at the output. Using that, they were able to improve upon the original Kennedy receiver by a little bit, but not all the way to the minimum error probability, the Hellstrom bound. So what it suggests, and this is an open problem, that for the Doliner receiver, we had two states that had different mean. Okay, so alpha and minus alpha, they were centered at a different point in the phase space. And that's why playing with displacement enabled us to get this minimum error probability by playing with the photo detection, post-detection statistics. If you had two zero mean states, for instance, let's say I gave you the two hypotheses as being vacuum and squeezed vacuum, okay? So both have exactly the same mean, but one has squeezing, the other one does not. Such a situation, it seems plausible that a Doliner-like receiver, but one which does not play with the displacement, but plays with an adaptive squeezing and photon number, might be able to get you to the quantum limit. This is just a conjecture, but in a paper a couple of years, actually last year, Jeff Shapiro's group, and this was from Chuntao Zhuang, Jeff's student, he showed that for a particular binary state discrimination task involving two zero mean Gaussian states, that such a squeezing like Doliner receiver, so where if you're using a Doliner-like strategy where you are toggling between applying a different squeezing schedule, but you're not playing with displacement at all, gets them to the minimum error probability of discrimination for that. But whether or not displacement, squeezing, and photon counting put together using an adaptive strategy can get you to the quantum limit of phase discrimination remains an open problem. But the nice thing is that these three things make a universal toolkit, meaning in principle, you can design arbitrary unitaries and arbitrary measurements with these. So the general circuit synthesis problem is very hard. Understanding linear optics and squeezing, which are called Gaussian resources, they are not universal, but understanding how to decompose an arbitrary circuit involving these Gaussian resources is known. But the moment you include any non-Gaussian resource, like a Kerr nonlinearity or photon counting or single photon sources, it becomes universal, meaning all Gaussian resources plus any one non-Gaussian resource makes it universal. But understanding the circuit synthesis for arbitrary non-Gaussian or arbitrary universal operations is open. There has been a lot of work starting from, I would say, Seth Lloyd's 95 paper and this famous Brownstein and Lloyd paper in 99 on understanding this circuit synthesis task of, in a lot of quantum information theory results applied to optical communication problems, you will end up with an operator description of an optimal measurement or an optimal unitary. But how do you take that and translate that into elements that come from this universal set is very hard. People have played with single photon addition and single photon subtraction as systematic tools to understanding degaussification and universal unitary and measurement creation. There is a vast literature on this, but I'll just point you to some papers that you might find interesting. In this paper with Lixiong Zheng and Haiwan Chang, we showed that very strong evidence to the fact that a Dolinar-like receiver will not work for ternary discrimination and beyond. So I think this would be a natural stopping point for the last part, which is slightly shorter than the first two, where we will apply tools that we have learned so far to understand quantum limits of optical communications. Okay, so let's start with the third part of the tutorial. And in this part, we are going to put together material we have learned about quantum notation and optical detection theory into understanding limits of communications capacity. So let's start with the very simple example we have been playing around with BPSK in the last part. And I'm going to start working with the physical channel being an identity channel, a lossless, noiseless optical channel, meaning if I send a coherent state alpha at the input, it appears as the coherent state alpha at the output. And later on in this part, I'm going to introduce loss and noise in the channel. Okay, so this is the physical channel, and you are transmitting, and then you have a receiver. So we are going to focus on the receiver part. So let's say I use a binary modulation, alpha and minus alpha, and I use one of these receivers we have learned so far. So we have seen the homodyne receiver, we have seen the Dolinar receiver, and both of these produce symmetric errors, meaning if I send alpha, the probability that you will guess minus alpha is same as the probability that you will guess alpha if minus alpha was sent. So both of these will induce a binary symmetric channel, just that the formula for P as a function of the mean photon number n is different. Okay, so depending upon which one of these two receivers we pick, we will have a different binary symmetric channel, and that will have a different capacity, and the capacity in either case will be 1 minus binary entropy of P. Okay. Now let us plot these capacities. So we have seen these plots before, the error probability as a function of n. So what I'm showing here is the black line is the Kennedy receiver for BPSK, which I actually hadn't shown you before. Remember, we only wrote down the expression for error probability for the Kennedy receiver when beta was equals to 0. But when you optimize over the choice of beta, you get this black line. This pink line is the probability of error for the homodyne receiver. And this red line is the minimum error probability attained by the Dolinar receiver. The channels induced by these receivers, all of them are not binary symmetric. So homodyne and Dolinar, they both induce binary symmetric channels. So the capacities are just the 1 minus the binary entropy of that error probability. But for the Kennedy receiver, your channel, it's still a 2 input, 2 output channel, but these errors are not symmetric as we saw previously. But when you do the capacity calculation and optimize over the prior probability distribution, you get these curves. So this is capacity for homodyne, this is Kennedy, which does, now you see that it does strictly better. Dolinar, this was our C1 capacity, and this is C infinity. We haven't talked about what receivers will we need to use to get that. So one thing that should jump out of these two comparisons is that demodulation error and capacity, they don't go hand in hand. If you try to minimize your error probability of discriminating between the states, that is not necessarily the same one that will maximize capacity, because there is a prior probability, and the way the whole channel statistics plays into the capacity calculation can be more complex. Okay, so let's take that capacity curve. So I dropped one of those. So I'm plotting the three, homodyne, Dolinar, and the Holevo limit. This is the C infinity. And instead of plotting capacity as a function of sigma, which is the overlap between the coherent states, e to the minus 2n, I'm going to plot the capacity in units of bits per photon. So C of n is the bits per pulse, bits per BPSK pulse, which is what we were plotting so far, divided by the number of photons per pulse. So this is your bits per photon, and this is mean photon number n. So now see, something interesting happens, that both the Dolinar receiver and the homodyne detection receiver, their bits per photon caps off at a certain value. So this is 2.89, just 2 log 2. But the bits per photon attained by the optimal receiver goes to infinity as n goes to 0. So this blue is C1 and this black is C infinity. So, and this ratio was what I was talking about that goes to infinity. So, that sigma, the overlap between alphas, they translate to the mean photon number using that formula. So, there is a big gap between these two. And in order to bridge that gap, we need joint detection receivers. We need to detect multiple pulses at once before you do any further post-processing. The moment I transduce one optical modulated pulse at the output of the channel, bring it to the electrical domain. If I do that on a channel use by channel use basis, I'm done. I'm already stuck below C1. In order to go beyond C1, you have to do more than that. So let's take this example. So you probably remember this circuit from when we were discussing USD measurements. Okay, so we had one of these two inputs, so alpha minus alpha and minus alpha alpha, and depending upon which one of these you put in here, you will get these three different outputs. So I'm sorry, I misspoke. So I'm now taking three possible 2 more BPSK code words. So I have 3 possible 2 symbol code words. So think of this, the 2 inputs of this beam splitter as 2 uses of that underlying channel. And I'm going to give myself only 3 of the 4 possible things I can send. So I'm constructing an inner modulation code for myself. Every 2 successive uses of the channel, I'm not going to allow 1 possible combination of the 4 possible combinations. So I know my receiver knows that to expect one of these 3. I'm going to first feed it into the beam splitter. What will I get? If this was sent, I'll get all photons here. If this was sent, I'll get all photons here. If this was sent, I'm going to get all photons in here, but with a minus sign. Okay. So what could we do now? Well, we could put a photon counter over here. If that clicks, I know that it has to come from x equals to 1, right? Because these 2 are 0. If it does not generate a click, then I could turn on a Dolinar receiver to discriminate between these 2 BPSK pulses. It's just a BPSK with a different amplitude, square root of 2 alpha. Okay, so let's do that calculation. So if you do that calculation, you would get a transition matrix that looks like this. Okay, 1 minus e to the minus 2n is the probability that you will get a click if the first hypothesis was sent, this hypothesis. And if you get that click, you will know that for sure. You will never make an error. If you don't get a click on that one, you will turn on a Dolinar receiver. And this is the crossover matrix. This is the transition probability matrix of the Dolinar receiver you will get to discriminate between square root of 2 alpha and square root of 2 minus 2 alpha, minus square root of 2 alpha, and q is equals to that. Okay. The reason you get these 2 is that if you do actually send the first input, meaning if you send this particular input and you don't get a click because of the Poisson probability distribution, and you still will turn on the Dolinar receiver because you don't know why you didn't get a click, you will choose between 2 and 3 with equal probability. So your error will get equally spread between 2 and 3. So anyway, so we take this transition matrix and we can write down the mutual information of that transition matrix. This is now a Shannon capacity calculation. We can do that, optimize over the prior probability, p 1 minus p over 2 and 1 minus p over 2 is what I'm giving as the priors. And I'm going to divide it by 2 to get my bits per symbol. And when I do that calculation and plot it, this is what I get. So this was our C1. This was the C infinity that I had shown, expressed in bits per photon as a function of n. And you get a tiny little bit of better capacity than C1. So this is R2 over n. And this is related to the problem I was talking about this morning, that we don't know C2, but R2 as a function of n when n goes to 0 for that particular receiver design gets you about 2.5% higher capacity than C1. It's a fundamental capacity benefit. It's a superadditive capacity. Okay, so now one can say, so aside from the fact that we don't know C2, what else could we have done instead of building that physical receiver? So that receiver that I showed you, this design, this joint detection receiver gives us R2 over C1 as 1.0249, okay? But think of the state discrimination task that we talked about in the previous part of the lecture. So if my job was not to do communication capacity maximization, I just wanted to minimize the error of choosing between them, then I could calculate the YKL measurement, right? The measurement that minimizes the error probability. And what did we say? That measurement is a projective measurement with 3 outcomes, with the 3 vectors positioned with respect to the state vectors in the optimal way so as to minimize the average error probability. I'm going to calculate that measurement, but calculate the mutual information attained by the transition matrix induced by that measurement. And when I do that and do the calculation of the R2 over C1, I get a little bit higher capacity improvement, 1.0266, which again, no intuition here. This measurement was not supposed to maximize capacity. It was supposed to minimize the error probability. Okay. Now, something I did in this paper over here was we said, well, forget about the YKL measurement. Just do it numerically. Just take 3 states, your 3 states that your 3 2-symbol code words, and take a 3-element projective measurement and position that with respect to your state vectors in the most optimal way, where optimal is in terms of maximizing the mutual information between the input and the output, okay, and maximize over the priors. And then I got a little bit better R2. But then that also I don't know if that is C2. Why? Because if I am presented with 3 pure states, in general, the mutual information maximizing measurement could have 6 elements, and it could be a POVM. It doesn't even have to be a projective measurement. And this was a special case of a result from Peter Shore in 2000. So this C2 for the BPSK case and a receiver design still remains open. But let's take a step back and look at the system picture of what it will look like if you were to build this joint detection receiver. So you have your information to be transmitted coming here. You have an encoder. Your encoder will take blocks of your, so this is your code, okay, so it's taking your chopping up your input symbol transmission sequence and mapping them into a code that comes from 3 alphabets, because the channel you have induced has 3 inputs, right? So you will map these to 1, 2, or 3. This is your coded transmission. Then it goes into your channel, but that channel is not the original channel. It's now the channel that is induced by that physical channel, which could be a lossy channel or an identity channel, and the choice of your receiver. So this whole thing is your P of y given x, which is a 3x3 transition matrix, and you get noise because sometimes you make noisy decisions, and then the decoder maps it back to your information transmission that gets decoded out. So the actual sequence that goes into your physical channel over here, it never has minus alpha because we prohibited it. So the sequence of alphas and minus alphas are always, they go in blocks of 2. Okay, so this is the concept that we will now need to build build bigger and bigger receivers. Okay, so we have talked about this several times, but I just wanted to say it again that no physical detection, optical to electrical conversion, physically permissible, acting on one BPSK symbol of the received code word at a time, could induce a channel P of y given x whose Shannon capacity would exceed C1. So this includes any feedback, feed forward, any soft information processing, anything. Okay, if you detect one symbol at a time, you are limited to C1. Noise is added at the detector. When we talk about the AWGN channel model, all of that channel, it's the receiver that adds that noise, most of the noise at least. So the only way to avoid that noise, well, we cannot really avoid it. Only way you can position the information bearing light in the best way to that inevitable detector noise is to do some optical domain pre-processing. And calculating the quantum limit to capacity is relatively easy, but finding receiver designs is the harder problem. We saw this picture in the first part of the lecture today. So what's just happening is that this joint detection receiver is letting you pack in more number of code word waveforms that can be discriminated by a receiver acting on those whole waveforms collectively. Okay, so now we are not thinking in terms of Hamming weight anymore. So that's the main difference. Meaning, if I choose the Dolliner receiver, then I can use, say, any code designed for the binary symmetric channel, and there your decoder will just do a minimum distance decoding, trying to get to that capacity, right? But what's happening here is that when I'm not using the Dolliner receiver, when I'm using this Holevo capacity achieving receiver, my measurement is directly acting on the sequence of alphas and minus alphas. Okay, and if you let yourself do that, then you can pack in more of these that you can discriminate exactly with 0 error probability or close to 0 error probability as n goes to infinity. Let's take one more example and try to build another receiver that gets more superadditive capacity than what we have seen so far. Okay, so this was a transformation we had seen earlier. Again, that same circuit we used for the UST receiver. So alpha, alpha, alpha minus alpha goes through a beam splitter to give me the coherent states over here. I can think of this transformation as 2 Hadamard matrices multiplying each other. So this beam splitter with a transmissivity 1/2 is just this unitary, 1, 1, 1, minus 1. When I multiply that by alpha minus alpha, I get 0 square root of 2 alpha, which means I'm multiplying this by a 1 minus 1 vector, and multiplying, and I'm sending in alpha alpha, then I'm sending in a 1 1 vector. So two Hadamard matrices multiplied together gives us the identity, and what is happening over here can be thought of as two Hadamard matrices multiplying each other, except that instead of 1 over square root of 2, I have alpha over here. So alpha alpha times this beam splitter gives me square root of 2 alpha 0. Alpha minus alpha times this beam splitter gives us 0 square root of 2 alpha. It's clear? Okay. So let's build this forward. So let's say we had now 4 coherent states. We know that Hadamard matrices, they multiply to give identity, and that's not just true for 2 by 2, it's true for 4 by 4, 8 by 8, and so on, right? I can write two 4 by 4 Hadamard matrices and get identity. All that means is that I can decompose that into 4 beam splitters now, and depending upon which one of these Hadamard sequences I send, all my photons are going to appear at one of these 4 outputs. It's a fairly simple calculation. In fact, you can see that by composing 2 by 2 Hadamard matrices to get a 4 by 4 Hadamard matrix. Now, note that here, if I were to put in detectors at these outputs, what will happen? If I choose one of these 4 code words and I get a click in one of these outputs, I will know for sure that that particular code word was sent. And it could not have come from any other detector, again assuming ideal detectors and everything is ideal. So, and if I don't get a click in any 4 of these detectors, I have an erasure outcome. I don't know what was sent. So I have constructed ourselves a USD measurement strategy when I am presenting the detector or receiver in this case with one of several Hadamard coded BPSK code words. Now, if we were to do this for higher and higher code word blocks, so this is, I'm just showing this picture 8, you can keep drawing these beam splitter circuits, and this goes back to your question earlier today. Let's see, this is an n by n circuit which requires me n log n over 2 beam splitters. I don't need n square beam splitters because this is a special class of unitary matrices. So for 8 by 8, I only need 8 log 8 over 2, which is 12 beam splitters. So let's do a capacity calculation, which is not too hard because my P of y given x induced now is simply this. My x is over now n possible inputs, where each input corresponds to one of these Hadamard code words. And with the probability e to the minus n times n, capital N is the mean photon number in the alpha, and n is the number of coherent states you have. So when all of these appear at one of the outputs, your total number of photons at this output is n times n. So the probability you won't get a click is e to the minus nn. This is what I'm going to call my erasure output, the n plus 1th output. And if I don't get a click, if I do get a click, then I have the right output, which is the case when my input is same as the output. So y equals to x with this probability 1 minus e to the minus nn. And I'll never make a wrong detection. This is what the second line is showing. So if I will never say 4 if 1 was sent. So now I can do a mutual information calculation. It's a very simple calculation. You can derive this just in a couple of lines. You will get this answer. But this mutual information is of a channel that consumed little n uses of the underlying channel. So I need to divide this by little n. So let's do that. So we divide it by little n in order to get bits per mode or bits per BPSK symbol. And now if I plot its bits per photon divided by n, just to see it in this picture, you get this green line. Okay. So this was C1 and that was my R2. This is C infinity, and this is what we get with Hadamard coded BPSK inputs and this particular green machine joint detection receiver. We are not yet at the Holevo capacity. Okay. But so far I've been able to tell you the operation of this receiver and analyze everything using semi-classical theory. All I was still using is beam splitters and Poisson noise. I did not use anything other than that. Okay. So we then ask ourselves a question, is there a semi-classical limit to capacity? Meaning, if your receiver uses the most general form of pre-processing that uses beam splitters, local oscillator, coherent states, and feedback, feed-forward, photon counting, but only these resources that can be described semi-classically, is there a fundamental limit that you cannot cross? And this was found in this paper over here last year, that this semi-classical limit to capacity if you in the low photon number regime, this is the difference between the Holevo capacity and this semi-classical limit appears in the second order term when you write down the Taylor series expansion in the low photon number limit. So both of these capacities, this is our green machine, which can be described semi-classically. This capacity is given by n log of 1 over n. Ns is the mean photon number. This is what I was calling n, I'm sorry for the notation. And the second term for Holevo capacity is plus n, whereas for the semi-classical limit, you get minus n log 1 over n. Okay, so now this black line was the BPSK Holevo limit. This blue line is the Holevo limit for an unrestricted alphabet. BPSK is a very restrictive alphabet. So we calculated this capacity in this paper in 2004. So when ns is small, you see that there is no difference between these two, meaning binary modulation is sufficient, which is not, I mean, it is intuitive. When ns is so small, why use multiple constellation points? Binary constellation is already optimal. So what would it take to bridge the gap? So some sort of a generalized Doliner-like receiver is meaning a receiver of this kind that we analyzed in this paper, which uses arbitrary passive linear optics and Doliner-like feed-forward strategy does not, and we argue why this is the most general thing to draw for this Doliner-like receiver that acts on multiple code word symbols at a time, is limited still to this scaling. So in order to go beyond that, you need to truly do something quantum, like squeezing, for instance, which we don't know how to build. Okay, so let's now move away from the pure identity channel. If you have loss in your channel, it can be modeled by a beam splitter. So if I send alpha, you will get square root of eta at alpha at the output. So now the nice thing is that with loss, a coherent state remains a coherent state. So if I send n photons here, I'll get eta n photons at the output. So I can simply talk in terms of the received photon number. I don't have to talk about in terms of the input photon number. And now if you calculate the Holevo capacity, if I used a coherent state transmission, this is a very simple calculation to do, because if I send a coherent state transmission, and with that particular input distribution, the Gaussian input distribution with mean photon number n, I can write down the average density operator. Okay, this average density operator happens to be a thermal state, and the von Neumann entropy of that average density operator gives us this g of x function. Okay, and this is a pure state, so you don't have that second term in the Holevo capacity expression. So in the Holevo capacity, if you remember, we had an entropy of the average output state minus the average of the entropies of the individual output states. So the individual output states are pure, so that term is 0. So this capacity, this is how we calculate the capacity. But you can also show that no other distribution attains a higher capacity, and no other states like coherence, squeeze states or number states, they attain a higher capacity, meaning coherent state transmission is the optimal. Product coherent state transmission is optimal. Coherent states are the only pure states that remain pure at the output of a lossy bosonic channel, and they only go through this attenuation in the amplitude. So this is why so far the fact that we have been working with an identity channel with n being the mean photon number at the output is justified, because we were already in effect, we were including any loss in the channel, because we were just talking about the mean photon number at the output. The proof of why this is the coherent state transmission is optimal, this was done in this paper. The details are not so important for the purposes of today's tutorial, but the achievability is something I just showed you. This is the von Neumann entropy of the average output state when I send a Gaussian modulated input at the, with coherent state input. The converse follows from upper bounding this Holevo quantity by maximizing the first term and minimizing the second term individually. Okay, and the maximum of the first term is given by this function, because the maximum von Neumann entropy of a state is given by the g function of the mean photon number at that state. And the mean photon number, if I put in ns photons, I'll get eta ns photons regardless of what state I actually used. And the minimum of the output of this term, the average of the von Neumann entropies at the output, can be further lower bounded by just the minimum output entropy of the channel. And since putting 0 here will give me 0 here, which has entropy 0, so the minimum is trivially 0, so that's what got us the capacity, which exactly matched the achievability. So this is how we prove the capacity, and then we try to prove the same exact capacity when instead of vacuum you have thermal noise in the other port. So if you have loss and noise in the channel, then on the other port you put in thermal noise, The achievability still is simple. You use coherent state with a Gaussian modulation. Now you get two terms. The second term is no longer 0. But when you try to do the converse, you get the same exact term over here at the output. This is the minimum entropy at the output, meaning what state can I send at the input that will minimize the von Neumann entropy at the output if a thermal state is going in here. This was conjectured in this 2004 paper that we wrote to be the entropy that you will get if I put in vacuum at the input. But that conjecture, it turned out to be a notoriously hard thing to prove, and it remained open for 10 years, and it was proven in 2014 by a few people, including Holevo and Vittorio Giovanetti, Raul Garcia Patron, Nicolas Cerf. And they proved that our conjecture was indeed true, and hence this is the capacity of the lossy bosonic channel with thermal noise. What if we use the homodyne detection receiver at the output? Send alpha, I'll get this is my noise statistics. We saw that in the morning. So you have an AWGN channel. So you have introduced, by doing homodyne detection, I have induced an AWGN channel whose capacity is just 1/2 log of 1 plus the signal to noise ratio. Signal power divided by the noise variance. And that's this many bits per mode. What if I use heterodyne detection? I will get now, I have two channels because I can encode information both in the real and in the imaginary part, but I have more noise in both of those. So that 1/2 factor goes away from the front because I have two of these things I'm adding. But the noise term, instead of 4n, it becomes n. So your signal to noise ratio is worse. So when you plot these capacities, what you see is that there is a crossover that happens between homodyne and heterodyne capacities. And this has actually been known for a long time, that when you are in the power limited regime, when n is small, you are better off putting all your energy in just one quadrature and live with that better noise variance. And when you go to higher power, you are in what is called the bandwidth limited regime, where it's better to split up your power, put it on two channels, and take the hit of the extra noise you get on the two channels. And you get a better capacity that way. And this is G of n, the ultimate Holevo capacity. And heterodyne detection's capacity becomes asymptotically optimal when n becomes high, meaning the ratio of these two become they get closer and closer to 1 as n goes to infinity. Okay, so now capacity increases indefinitely, as I said, with increasing input power. So we must use higher order constellation in order to keep up with that, right? So we have been only talking about BPSK constellation. That's a topic I'm completely going to skip right now, but I'll just show you the results. So here is a plot where I'm plotting things in a slightly unconventional way. So C of n is what we have been calculating so far. So that's our capacity in bits per pulse or bits per channel use. And this is bits per pulse divided by mean photon number per pulse. So this is the photon efficiency. So the x-axis is how fast you send information, and y-axis is how efficiently you encode information in your photon. And there is a trade-off between the two. You can't do both at the same time. If you try to be very efficient with respect to your encoding, you have to be lower spectral efficiency, send your data slower. And for low n bar, you are pushed in this regime. High n, you are pushed in this regime. This is the Holevo capacity. And all of the non-black lines that I am using here, that's my convention, they correspond to receivers we have talked about in this tutorial today. All of these structured receiver designs. Heterodyne detection wins over here. Homodyne sort of wins over in the middle. This green line is the Dolinar receiver. And this is direct detection, photon counting. And these are the only three standard optical receivers. And as you see, there's a gap between this and the Holevo limit. So all the other black lines we are not going to talk about in this lecture today. So what receiver actually attains the Holevo capacity? Well, so there is a measurement that appeared in Holevo's, the Holevo Schumacher Westmoreland paper, the square root measurement. And I decided not to talk about it because this is something you can read up in any information theory book, including Mark Wilde's book talks about that. This is a measurement that is described mathematically as a set of POVM elements that are functions of your code book, of the states that you choose to be your code word states. You can write it down, but we don't know how to design a receiver to implement that measurement. One thing I should say before I get into that is that if you were able to figure out a receiver that discriminates between those 2 to the nr code words optimally, then you would attain the Holevo capacity. Meaning, if you are able to figure out the minimum probability of error receiver, the YKL measurement for those code word states, you can get to the Holevo capacity. And the code words, you know the code words, so you can evaluate the Gram matrix, the relative inner products. But So that's why understanding how to go from 2 to 3 to the more general case will help us also in attaining channel capacity. A receiver that designed that Mark and I and Seth Lloyd and Sihui Tan, we looked at, this is, I'm going to briefly talk about that, and this is the last topic I'll mention today, is the vacuum or not measurement. So vacuum or not is this measurement that is described by just these two projectors, 0, 0 and identity minus 0, 0. Okay. So that's a legitimate measurement. But we don't know how to design a measurement to do that, but let's take a state psi. If you were to do this measurement on this state, I'm going to get the 0 outcome with probability magnitude C0 square, which is the coefficient sitting in terms of 0. And with 1 minus that probability, I'm going to get the state psi projected onto this projector, which happens to be the same state as psi, except that the vacuum term is taken away. So it's CKK. K goes from 1 to infinity, and I need this normalization term in order to make sure this is still a legitimate unit norm state. If you could design this, we don't know how to design a receiver that does this, but quantum mechanics tells us that this projector is a legitimate measurement. If we could do that, but for n modes, meaning if I have, say, for instance, 2 modes, alpha minus alpha, and if I had a 2-mode vacuum or not measurement, meaning n equals to 2, I would project it with probability e to the minus 2 magnitude alpha square to vacuum vacuum, and with 1 minus that probability, I'll project this to this funny state where I'm summing off the vacuum component from alpha minus alpha. So this is an entangled state. So your measurement will produce an entangled state even though your input is a product state. Okay. If we could do it for n channel uses, then we have a receiver design which iteratively tries to null your code word and ask whether you have all vacuum or not, which achieves the Holevo capacity. So you have 2 to the nr code words. Your receiver starts with the first code word being the belief that that code word was received. It applies nulling. Remember, we talked about nulling in the context of Kennedy receivers. It brings it down to 0, 0, 0, 0, 0, 0 if that first code word was received. You are subtracting off all the amplitudes. And then present that nulled code word to this vacuum or not box. Ask it, is it vacuum, tensor n, or not? If you get the yes answer, you stop there and declare that is your win. If the receiver says it is not vacuum tensor n, then you undisplace it back to the code word. You don't know which code word you got. You just undisplace it back, and it displaces it by the negative of the second code word in your list, so that if it were the second code word, you will bring it to vacuum, present it again to the vacuum or not black box, and you keep going. And the first time your vacuum or not box says, I got vacuum, that was the code word that your receiver outputs. When you do the analysis, you can show that this receiver will achieve the Holevo limit. Mark and I worked on quantum polar codes to achieve the Holevo capacity of a general classical quantum channel, which would apply to this BPSK channel we talked about. But the successive cancellation decoder, that itself is a joint detection receiver. So, no surprise, it has to apply on multiple channel symbols to work at a time in order to get to Holevo capacity. We looked at efficient joint measurements when your codes have certain symmetries. This was a work led by my colleague Hari Crovey. And in this paper was our, I would say, a half-hearted attempt at the time of trying to do something that gets you to the minimum probability of error limit of for arbitrary number of coherent states. The reason I said it was half-hearted, I mean, we got to a point where we were able to show that you can reduce that optimal measurement to something that looks like, at the end of the day, a small quantum computer. So if you had an all-optical quantum computer that could do arbitrary logic on single-rail qubits, and these are terms we have not introduced today, then you would be able to get to the minimum probability of error discrimination between arbitrary coherent states, which will in turn get you to the Holevo capacity limit. You can also do finite rate corrections. This is Holevo capacity. You can define something called, just an analogy to Yuri Polyansky's work on classical communication, you can introduce a dispersion quantity. It was done by Marco Thomas Michel and others. Then Mark and I, we generalized that to the bosonic channel with Joe Rennes. You get a finite length correction. This is the bits per mode that you can send as a function of the error probability of demodulation of your message and your block length n. And as I said that semi-classical conditional nulling receivers, they don't work. They don't get you to this high, this Holevo capacity. But these receivers that gives you this better error exponent from e to the minus n over 2 for heterodyne to e to the 2n, we saw all these examples of Kennedy-like receivers that gives you this better error exponent. Clearly, they don't work to get you the capacity, but what they do is that these receivers get you a better error exponent, meaning they get you a better dispersion or a finite length performance. And again, something I'm not going to talk about today. So let's skip this part about free space optical communications. This is where I was going to tell you how to, what those etas are, the channel transmissivities. But in this slide, what I'm showing here is that if I had m parallel channels, m parallel beam splitters, okay, and if I did the same plot between bits per second per hertz and bits per photon, and I plotting here the capacities attained by the Holevo capacity and the on-off keying with direct detection, in order to get to a certain performance of bits per photon and bits per second per hertz, what it will translate to is that you will need many fewer modes, many fewer channels to attain the same capacity performance if you had that joint detection receiver. So this is a plot from a calculation we did that was inspired by free space communication in the near field regime. So instead of 4,500 modes, you will need about 189 spatial modes, which will translate to smaller apertures or longer distance, whichever way you might want to think about it, that will get you the same performance. Okay, so this brings me to the end of the tutorial. So we are almost right on time. So just a recap, this was not a tutorial on quantum information theory. We used tools from quantum information theory. I hope I was able to impress upon you that quantum information theory gives us very powerful tools to calculate fundamental limits of communication capacity. We did not talk about estimation problems, but this is true also for estimation problems with applications to imaging and sensing. But oftentimes it does not tell us how to design a physical receiver that gets you to that performance. But the main important thing we saw today was that the y in the P of y given x, where all of Shannon information theory starts, is a very strong function of the receiver. And a receiver, as I said in my first slide today, is a combination of optical domain preprocessing, the detection, and post-detection electronic domain processing. So receiver designs have that detection part preceded by that all optical processing has a huge role to play in inducing that Y. So once you have a stochastic description of your channel, then all of standard classical information estimation theory applies. The other thing we saw today, and this is something that we did not go that much into detail, but we saw some examples where if you just stay within things that can be described using semi-classical theory of photodetection, things like beam splitters, phase shifters, Poisson noise process that comes from a direct detection of a laser pulse, it appears that there is a fundamental limit to how far you can push the capacity performance. And in order to understand how to build receivers that gets you to the fundamental quantum limit of capacity, we need a universal toolbox. And in order to complete a universal toolbox, when you do have photon counting and linear optics, you need to put squeezing in that mix. And understanding how to do the general circuit synthesis problem is very, very hard when you have non-Gaussian unitaries and non-Gaussian measurements. And this translating multimode unitaries and multimode measurements that often come from quantum information theory calculations to a physical receiver design is that circuit synthesis part, which is very hard. Even within those non-Gaussian resources, there is a trade-off between offline and inline non-Gaussian resources. We talked about squeezing as a resource. That's an inline resource, meaning you are putting the light through a squeezer to do something to it. But there are other ways to inject the non-Gaussianity needed to get you that universal power. One example being, you prepare single photon Fock states, just one photon in the pulse, and use that as an ancillary resource. That's a non-Gaussian resource. And there are ways to prepare single photons that experimentalists are working on. If you inject that single photon in an otherwise linear optical circuit with your code word that you are trying to demodulate, that also can give you that non-Gaussianness that you need. And sometimes in some contexts might even be easier to do that compared to inline non-Gaussianness. There are people who worry about they are doing research on understanding the trade-off between inline and on offline, and both problems feed into this general circuit synthesis problem. I did not talk about multi-user information theory at all. In my PhD thesis, we had looked at the capacity, the quantum limited capacity region for classical communications for broadcast channels, and we can calculate those quantum limits of capacity. But in the general case, when you have loss and noise in the broadcast channel, in order to prove that the capacity region I had in my thesis, which used coherent states and a Gaussian modulation, in order to prove that that is indeed the capacity, you will need to prove a quantum version of the entropy power inequality. And that quantum version of the entropy power inequality reduces to that minimum output entropy conjecture for this single user lossy noisy channel that I spoke about, which was proven in 2014. But the general quantum entropy power inequality remains open. And we did not talk much about the code design, although I did mention Marx in my work on quantum polar codes. So I think I'm going to stop here and take any questions if you have. The fourth part, which I knew that I was not going to get into, was quantum secured communications. But we can talk about it offline if you're interested. Thank you. It was a long 3 hours. If you have any questions, I'm happy to answer. Oh, by the way, before I go into questions, two of you gave me your email addresses. So for the slides, if you would like, please, the copy of the slides, please feel free to send me your email address. I will post these slides on my website, and I'll point you to that. It might be too big to send you over email, but I'll send you the link. Okay. Any question? You had a question?
So everything we talked about today, is it something specific to deep space optical communications, or is it also true for fiber optics?
The question was, what we talked about today, was it specific to deep space, or does it apply to fiber optical communications? So all that I talked about today is completely general. As long as your channel can be thought of as a concatenation of beam splitters, which it always can be, this theory can be applied. The reason this is probably more relevant to deep space communications is because the gap in capacity that you saw between the classical or standard receiver designs and the Holevo capacity, if you see, this gap is much wider in the low photon number regime. When you go to the high photon number regime, these two lines, the ratio between these two become 1. So fiber optical communication is often working way over in this regime. That's why you would see a lot of work on heterodyne detection with 8 PSK or QAM modulation that is trying to push the capacity in the high photon number regime. So in that regime, building joint detection receivers may not give you any capacity benefit. Although, as I mentioned towards the end of my talk, Kennedy-like receivers that uses nulling and feed forward that can give you a lower demodulation error rate, a higher error exponent to the demodulation of the error rate, which can translate to a better finite block length performance, not necessarily capacity benefit. But the theory itself is completely general. So this part that I did not speak about, free space communications, if I have a transmitter aperture and a receiver aperture, area AT and AR and distance L at some wavelength lambda, you can think of this channel as a set of infinite beam splitters, parallel beam splitters, where each of these beam splitters correspond to sending one spatial mode at the transmitter, and that spatial mode will appear at the receiver. Okay, and the normal modes of this channel, when you work out, they come out to be what are called prolate spheroidal wave functions. If I pick the first function and send that spatial mode through the channel, after you work out Fresnel diffraction through that channel length, only that mode will get excited at the receiver. So I can think of each one of them as parallel channels, but the transmissivities of those channels as I go to higher and higher order modes, they go down. So depending upon my length of the channel, I'll operate at a certain point. So if I am in the far field regime, which means that this number is much smaller than 1, then I only have my first mode that has any sufficient transmissivity. And the other modes over here, they have very close to 0 transmissivity, meaning they are useless channels. So I can, all that I develop can be used here as long as I know the values of eta m, I can apply this on.
This question, you think it also applies to the terahertz range near optical, for example, the range between 1 and 10 terahertz. So what's exactly the range of frequencies that can assume that the optical behavior holds? For example,
Good question.
here the 10 terahertz, you can go to terahertz communication. Can we work with these from here?
So the question was, what range of frequencies would it be legitimate to apply this theory that we talked about today? And the short answer is that in principle there is no restriction. Okay. However, when we talked about thermal noise over here, I injected a thermal state into the channel over here. Okay. So see this n of the mean photon number of the thermal noise that I'm putting into that beam splitter? That n is a function of your choice of the wavelength. So that n, the thermal noise per mode, is in terms of mean photon number per mode at say 1550 nanometer would be around 10 to the minus 5 to 10 to the minus 6 depending upon your conditions that you're operating in, daytime versus nighttime for a free space channel. If you go to the microwave domain, that number will be in the tens to hundreds of photons per mode. Okay, so that's a huge difference. So in the microwave domain, what happens is that thermal noise per mode is so high that some of these quantum benefits of joint detection receivers are completely wiped away, meaning doing a heterodyne receiver which induces an AWGN channel is probably the best thing or close to the best thing to do. So which is why you'd see all of this wireless information theory that you see in ISIT, the starting point of many of these analyses is AWGN, and that's perfectly justified because they're working at such a long wavelength that some of these quantum effects are completely washed away. On the other hand, there are groups, there is one group in Yale University led by Michel Devoret who are looking at microwave domain quantum operations such as squeezing, for instance. So squeezing is also called phase sensitive amplification. And people have demonstrated squeezing in the microwave domain. So there might be interesting things to be done at longer wavelengths using quantum tricks, but I would say the most relevant for all of what I talked about will be from visible all the way to perhaps mid-wave to long-wave infrared wavelengths. More questions? No?
So just to get an idea of practice, so currently for deep space optical, which receiver do?
So question is, currently for deep space optical communications, which receiver do people use? So for deep space communications, they use pulse position modulation and photon counting. So if I go to my PPM slide over here, where was it? Here. So they use this modulation format where M is around in the 256 is what the Lincoln Lab program that set up the Earth to Moon laser comm link they did. And they used a superconducting nanowire single photon detector, which is a form of single photon detector. So they are limited by this error probability, although they also had dark clicks from your detector. So that's what they currently use. NASA is currently working on, they started working on the Mars mission, and they have colleagues in JPL who I have spoken with, and they are designing laser comm systems which will go very similar way as they did for the lunar laser comm demonstration program. But interestingly, the gap between the Holevo capacity and the direct detection capacity widens as you go into deeper and deeper into the space, because the more the loss, the lower the photon number that you will receive at the receiver, and more the gap between those two will widen.
So it's roughly like a lower signal.
Sorry?
Roughly speaking, can we think of the photon number as SNR?
Roughly speaking, photon number can be thought as SNR, because photon number, remember that when you get a laser light pulse, you have no noise in it. Okay? All of the noise is added as a result of the detection. But think of homodyne detection. Homodyne detection gives us a signal to noise ratio of n over 1/4. 1/4 is that noise variance. So if your n is smaller, your SNR is going to go down. For direct detection, I cannot really think in terms of power over signal power over noise power, but I get a Poisson point process. But your ability to tell apart signals becomes lower if your signal power is smaller. So you're right that you can think of mean photon number received roughly as signal to noise ratio. Okay, I think we should probably stop here. We are about 15 minutes over, and thank you again for coming. And if you have any more questions, feel free to email me.